మీరు స్టేజే చూసుకోండి, ఇంకేమొద్దు. ఒకసారి ఏదైనా ప్లే చేసి సౌండ్ వస్తుంది టెస్ట్ అన్నిటికీ తీసుకొని ఫైల్ డెస్క్టాప్లో ప్లే చేద్దాం అనుకుంటున్నారా మీరు? అప్పుడు నేను డెస్క్టాప్ ఆడియో క్యాప్చర్ చేయాలి కాసేపు
దీని నుంచి వెళ్తుంది కదా
కొట్టుది
వేరే ప్లేయర్లో
ల్యాంప్ పెట్టుకోవాలి.
Windows 7 19 computer.
So, very good morning, ladies and gentlemen. On the behalf of Indian Institute of Petroleum and Energy, I extend a very warm welcome to each of you to the inaugural event of GIAN course on adsorption techniques for CO2 capture, modeling and simulation insights. We have with us today as our guest the Honorable Director of IIP Vishakhapatnam, Professor Shalivahan, Sri Ramphal Dwivedi, the Registrar, the Dean of Research and Development, Professor K. Vijay Kumar, then the foreign course instructor as Professor Devanshu Bhattacharya, the Indian course instructor as Ravi Chandra Datta, the local GIAN program instructor, Professor Rakamandal, and a heartily welcome to you all. So, to mark the beginning of this insightful gathering, we invite our distinct dignitaries to join for the ceremonial lamp lighting, a symbol of wisdom, knowledge, and enlightenment. May this light inspire meaningful discussions and groundbreaking ideas throughout the day. So I request you all. We will now present the virtual tour of IIP Visakhapatnam. This glimpse will show the vision and state-of-art facilities at IIP.
Situated on the shores of the Bay of Bengal, in the city of destiny, Visakhapatnam, the Indian Institute of Petroleum and Energy, IIPE, is an institution of national importance. It is the only energy-centric academic institute of the Government of India, where significant importance is given to research and education in energy. IIPE has set out to fulfill the dream of Atmanirbhar Bharat by making India's energy self-sufficient in renewable and non-renewable resources.
क्लाइमेट चेंज पर इस वैश्विक मंथन के बीच मैं भारत की ओर से इस चुनौती से निपटने के लिए 5 अमृत तत्व रखना चाहता हूं, पंचामृत की सौगात देना चाहता हूं।
To meet the global energy and climate challenges by providing the bunch of solutions espoused by our Honorable Prime Minister, IIPE seeks to turn India into a global energy hub. The Global Industrial Advisory Board of IIPE helps align the Institute's research initiatives with technological innovations. The thrust areas of IIPE's research are biofuels, batteries, carbon capture and sequestration, hydrogen production and storage, capture and conversion of CO2 into green fuels or EOR, renewable energy, waste to energy, and geothermal energy, among others. With industry partners, HPCL, NTPC, SBI Foundation, ONGC, IOCL, OIL, GAIN, Halliburton, and Greenco. The research activities help meet real-world needs of achieving a net zero goal and contribute significantly towards the United Nations Sustainable Development Goals of ensuring access to affordable, reliable, and sustainable modern-day energy for all. IIPE is executing a project in collaboration with NTPC to develop a 1-ton per day plant worth rupees 35 crores for hydrogen generation from seawater. This will fulfill the dream of Visakhapatnam becoming the first hydrogen city in India. The academic program of the Institute is aligned with NEP 2020, offering BTech, MTech, MSc, and PhD programs. The Institute enriches itself with an international academic board for framing the course structure. Some of the innovative academic initiatives are Sandwich PhD program, hosting foreign researchers, international electives, global student internship program, joint MBA with IIM Visakhapatnam, BTech MS program with US University, in energy education. IIPE provides fellowships to all undergraduate female students and a 70 to 100% tuition fee waiver for socially and economically weak students. It has initiated a student-faculty direct program to inculcate a culture of scientific curiosity among school children. It has also adopted a pledge to preserve ecosystems and sustain coastal communities and tourism. IIPE envisions strengthening and sustaining the region's socio-economic development, thereby contributing towards a Vincent Bharat. IIPE firmly believes in the stakeholders' ikigai or a sense of purpose. It strives to help foster blue zones, enabling a prosperous world to rise like a phoenix from the ashes of today's challenges. The new campus of the IIPE is coming up in Mamri Village, sprawling over an area of 201.8 acres. This campus will have state-of-the-art energy-centric research laboratories, including the Center for Net Zero, Center for Green Hydrogen, and Technology Center for Hydrogen Testing and Validation, along with academic, hostel, and other infrastructure buildings, with a total built area of approximately 60,000 square meters. Let us all come together and join hands to remain relevant and grow together.
So to commence today's proceeding, we now invite Professor Raka Mandal, the local coordinator, to provide an introduction to the GIAN program.
Hello and very good morning to all of you. So, as a local coordinator of IIP for the GIAN program, I would like to take this opportunity to introduce about this scheme. GIAN, or the Global Initiative of Academic Networks, is a program by the Ministry of Education, Government of India. It is designed to tap the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the institutes of higher education in India so as to augment the country's existing academic resources, accelerate the pace of quality reform, and elevate India's scientific and technological capacity to global excellence. The program was launched in 2015. After successful completion of 3 phases, the program faced a brief halt due to COVID pandemic. In 2023, it started again in form of phase 4 with double enthusiasm. In phase 1 to 3, among 2,163 approved courses, 1,848 courses were completed and delivery of more than 41,610 hours of lectures were carried out. With participation of more than 1,654 international faculty and 72,000 students, all 3 phases were grand success. In phase 4, which is the current phase, among 779 proposals submitted, 330 courses have been approved, and I am glad that 2 of them are from IIP. More than 2,470 lecture hours and 6,358 students are 2 prominent features of phase 4, and it just indicates the growing popularity of this program. Total 60 institutes and 87 international faculties have been involved in carrying out these programs. The faculties are from all over the world, not only from USA, Canada, Germany, France, and also from UAE, and recently we had faculties from Iran also. So the faculties are from all over the world. The courses are, this is the second course which is being carried out in IIP, and this course is specifically designed to train the personnel in application of adsorption technologies for reducing carbon dioxide emission and thereby addressing the issue of global warming. It will cover the fundamental principles of adsorption for carbon dioxide capture along with the recent advancements in the field. So far, there has been 50 registrations from both India and abroad, which is a very good indication, and including 40 offline participants and 10 online participants. The registrations complies from the undergraduate, postgraduate students, PhD scholars, industry professional, faculties, and this course contains 13 lectures and 9 new tutorials, and the representation from all over India, from the north to south and east to west, that just tells us that this is a center, this is growing in a popularity, and the acceptability of this topic and the importance of this topic for our course. Thank you so much for being here and extending welcome again once again to all of you. Thank you.
So thank you, ma'am, for your insightful words. Now, I would like to invite Professor Sridhar Palla, the course coordinator, to introduce us to the theme of this workshop, Adsorption Technique for CO2 Capture, Modeling and Simulation Insights.
Good morning, everyone. Respected Director, Registrar, Dean of R&D, course instructors, my colleagues, and the participants, I welcome everyone to the GIAN course on adsorption techniques for carbon dioxide capture, modeling, and simulation insights. So, first of all, I would like to thank GIAN for providing this opportunity and IIP for supporting us to conduct the event. Coming to the theme of this course, as we are aware that carbon dioxide that traps the heat, which is one of the reason behind this global warming. So there are several ways to mitigate the carbon dioxide emissions from the flue gases. Adsorption is one of the technique which is very old traditional chemical engineering technique. We have been using this technique for air separation, natural gas sweetening. So the idea is, why can't we use this old solution for the new problem? That is the idea behind this adsorption techniques for carbon dioxide capture. So as Professor Raka was telling, this course contains 13 lectures and 9 tutorials, where we cover the fundamentals of adsorption. In case any participants from different background, we will start with basics, and we will build the fundamentals on that. Then we will discuss what are the advancements that has been happened in this area and how to apply this technology for the carbon capture problems. So as we are aware that computational power has been rapidly increased these days for past few decades. So instead of conducting the time-consuming and expensive experimental studies, why can't we develop a models that could give us the same result? So in this course, we will show you how to develop models that could solve the carbon capture problems of the industries, and also we will show how to simulate those models on the computational tools that you will do during the hands-on sessions. So by end of this course, you will be in a position to develop your own models to any specific industry where CO2 capture can be done. And we received 50 registrations as mentioned. So I appreciate the effort of the participants traveled here to the Visakhapatnam in the middle of their semesters on the working days. So please utilize the time that you are spending here by interacting with our course instructors. And in case if you are facing any difficulty during the stay, we have very good organizing team. They are here to help you. You can reach them at any time. All the best. Thank you.
Thank you, sir, for such a wonderful explanation. Moving forward, I would like to invite Professor K. Vijay Kumar, the Dean of Research and Development, IIP, to address the gathering on the various R&D activities at IIP.
Good morning, everyone, and a warm welcome to the second GIAN course being conducted at IAPE. So the institute is very young, you would say, in terms of the number of years that we have taken to. But the kind of pace at which it has been growing, it is just now Dr. Bhattacharya was discussing, it's a kind of phenomenon. So we have seen the Prime Minister educating us the Panchamrit solutions to fight the climate change. So our director has also kind of promoted 5 Ps for the development of the institute: the publications, the projects, the patents, the partnerships, and most importantly, the PhDs. Because whatever the research that we do at the institute, that too, we being the energy-centric institute, the kind of research that is being done here is not only applicable to the national shores, but also to the global problems that we have been facing. So our purpose was to how we can take the science that is being done at IIPE to the people around. So for that, we have designed courses at different levels. So we have a summer internship program where we invite students, undergrad, grad students throughout India, and especially we are focusing on the less endowed institutes. So we try and select the students who are not really kind of accessibility to these kind of facilities and courses. So we deliberately we kind of select them so that they come and spend almost 4 to 6 weeks at IIPE, work on a focused problem, and they take back the knowledge that has been kind of generated here. Then we have the PhD Institute PhD program. Again, we select students absolutely based on the merit throughout India. So we give them the kind of fellowship that a government offers to any junior research fellow. And the third one is we have what we have seen in the video also, the local college and school student program. So again, here we invite students only from the government schools, which are not really kind of equipped with the kind of facilities which we ask for. So we invite them, they come and spend here 3 to 4 weeks, they interact, they are 9, 10, 11, 12 students. So they get really rejuvenated, minds get ignited in the kind of science that is being done, because again, we start from the fundamentals and tell them what has been done in the science of energy throughout the globe. So when they go back, and we have recently done the experience is kind of exhilarating, I would say, as not only for the students, but all of the faculty of IAPU who are involved, because the kind of the questions they were asking in the classrooms, the kind of doubts they were expressing, and the enthusiasm they have shown. So again, it's a brainchild of our director. And we are also training the faculty members of schools and colleges. That is another program, so that they are also exposed to the focused research that is being done, the advancement of the science that is being done. And the next one is the certificate courses. Recently, we have conducted a couple of certificate courses where, again, we invite people from the industries so that there will be industry academia collaboration will be taking place. The theory, the simulations that we create here, they can take into the real platform, and you can experiment with them so that we can, if something need to be improved upon here, we will be able to improve. And if they will be taking up the theories that have been developed at IIP and applying in the real world. And the next one is the GIAN's course. So again, I'm happy to note that earlier recently we conducted a GIAN course, the course 1, on the advanced membrane technology in the hydrogen energy. And this is the second one in the carbon capture. So as an energy-centric institute, we have to see to it that it is an anthropogenic induced problem, the carbon dioxide is. Either we should stop producing or we should stop mitigating that. So stopping production of carbon dioxide is probably may not be able to happen in another 200-300 years, because the kind of our dependency on the fossil fuels. So I am not sure that we will be able to stop the production of carbon dioxide. So the second solution that we are left with is decreasing that and converting into a useful product. Not only separating that, by adsorption and other techniques, but also converting into a useful product. That has been what the institute has been working. So in terms of the 5 Ps, because we have to take it to the people, that is the entire purpose of the PhD programs or the patents or the partnership. So it is the people to which we need to take all that stuff, and the GIAN course is one of the instrument in doing that. So I congratulate the coordinators, and also we are kindly, really obliged to our director for the kind of enthusiasm and the kind of encouragement he has been giving to the faculty. So a warm welcome to all of you to the city of destiny, the Visakhapatnam. I am sure that you will have a sumptuous meals of the course and also on the plate. Thank you very much.
So thank you, sir, for your such an inspiring words. Now, I would like to welcome Sri Ramphal Dwivedi, the Registrar of IIP Visakhapatnam, to share the insights on the institutional activities of IIP.
Good morning to all, respected dignitaries, faculty members, and participants. I extend a warm welcome to all the dignitaries and participants present here on the occasion of inaugural session of GIAN course on adsorption techniques for CO2 capture, that is modeling and simulation insights. Professor Sridhar Palla, coordinator of this course, Dr. Dibangshu Bhattacharya, international coordinator from West Virginia University, USA, and Dr. Ravi Chandra Datta, assistant professor of IIT Dharwad, as a national coordinator, has specifically designed this course to train the personnel in the application of adsorption techniques for reducing CO2 emissions, thereby addressing the issue of global warming. I would like to brief about the IIP. IIP is established in the year 2016 as an outcome of Andhra Pradesh Reorganization Act 2014. IIP is a specialized institute established by the Ministry of Petroleum and Government of India, and in 2016 it holds the prestigious status of being an institute of national importance at par with IITs and IIMs. The institute is dedicated to research and development in the energy sector with a focus on emerging areas. Our mission is twofold: to bridge the gap in the skilled manpower for petroleum and energy industries and to foster research excellence. At IIP, we offer 4 years degree program, that is a BTech program in petroleum engineering, chemical engineering, mechanical engineering, and MTech in energy engineering, and MSc in applied geology, and PhD courses in the relevant areas. Admission to BTech programs are based on the IIT JEE Advanced, while the MTech and PhD admissions are on GATE scores. And admission in MSc applied geology, we consider JAM score conducted by the IITs. Currently, we have 450 students, out of which more than 100 students are from PhD. The institute has very good record of placing the students. Last year also we achieved 100% placement, and this year also till now we have achieved the 92% placement, and the placements are still going on, and I hope this would be covering 100%. Our beautiful campus is coming up in Sabhavaram, around 40 kilometers from here, and 40 kilometers from this city of Vizag, and it will be equipped with the modern techniques, modern laboratories, research centers, and industry standard equipments to provide students and faculty hands-on training and research opportunities. Our esteemed faculty members, most of them having IIT backgrounds, are highly active in research and academic pursuits. See this GIAN course. On behalf of Institute, I convey my thanks to all the participants for becoming the part of this event, and also thanks to all faculty and non-faculty members who are directly and indirectly involved making this event successful. Thank you very much. Jai Hind.
Thank you, sir, for your address. Next, we are privileged to invite Professor Shali Vahan, the Honorable Director of IIP, to share his thoughts with us.
Professor Bhattacharya from Western Virginia University, Professor Ravi Datta from IIT Dharwad, Professor Sridhar Palla, Professor Raka Mandal, and the brand ambassadors of this course on adsorption techniques for CO2 capture, modeling, and simulation insights. I, on my personal behalf and behalf of the Institute, welcome you all to the GIAN course. I'll put on a very lighter note. And the problem is that you had seen a movie, you had seen the Dean R&D talking, you have heard the registrar talking, then what is left out for me? There's nothing, so I'll try to put in a very, very lighter stuff. Organizing this course by the end of March is one of the most toughest job in India. Financial year closing before the course started, we are pushing hard, both Professor Raka Mandal and Professor Sridhar. Yeah, you have to submit the bills. So most of the bills are coming in advance. That's one thing which is very, very tough job, let me tell you. Second thing is that, as Professor Bhattacharya is from Western Virginia, so I'll try to put the institute name with the Indian Institute of Petroleum and Energy. Looks to be governed by US because petroleum goes with the Republican and the energy goes with Democrat. So it's an institute which is supported by, I hope you'll agree to that. The second thing which talks about is the CO2 capture with the change in the US administration. Now the word climate change has gone to the carbon management. My personal experience with this has happened with two things. There's a group in ETH Zurich, they have a paper in Nature where they had directly captured this carbon dioxide at, I think, at Madrid airport, and they converted this to a synthetic kerosene, and which they tried to use it for the aviation. The second thing which has happened, we had gone to Oil India for CO2 UR. They said that why cannot to capture it directly and do that? Why to have extra investment of purchasing that and doing it? So I understand this topic to be very important, and I hope that some new thoughts would be coming up with this. The other thing is that we are going to celebrate our 10th anniversary with this October. So we have a lot of plans for that. And one plan is that with the support from all of you, the industry participants and people like Professor Bhattacharya, we have a plan to have international summer and winter schools. I'll request Professor Sridhar and Professor Raka to talk to Professor Bhattacharya to see that how it could be possible. We also have international electives and industrial electives. So the people from industry teaches that course. Right now it's one from the Gas Authority of India covering that course. Professor Vijay was talking about several initiatives. One of the initiatives which the board has approved is having a global internship program, which will be 75% of that would be paid internship, so 25%. So we are going to advertise very shortly. We also have a provision where the undergraduate program could be jointly mentored by faculties like Professor Bhattacharya and all. So these are some of the things which we are trying to do it, and we have done a couple of things which has really paid the fruits, and we expect that similarly these type of GIAN courses or the summer schools which we are thinking will be having more impact. And the stuff is that we need to reach to the people. One thing which really excites me here is the colleagues, they want to give back to the society. And that is why most of the things we try to do it for the government schools, not for the corporate schools or the public schools. With this, I once again welcome to this workshop. And I hope there will be a lot of important discussions would be. Only what scares me is this timing from 9 in the morning to 5 in the evening. Vizag is a beautiful city. I request the coordinators to give them some time so that they can see that. This is very scary. Thank you.
Thank you, sir, for such an enlightening address. Now, we are honored to have Professor Devanshu Bhattacharya among us as a distinct foreign course instructor. Professor Devanshu is a professor at the West Virginia University with extensive expertise in the advanced modeling and simulation, artificial intelligence, optimization, and energy systems. He has authored and co authored over 125 research articles, 5 book chapters, 300 oral presentations, and 60 poster presentations. His contributions to the field are truly commendable. Professor Bhattacharya, we request you to share your thought with us kindly.
I'm really privileged and honored to be here, and thanks for inviting me. And particularly, I would like to acknowledge Dr. Sridhar Palla to actually coordinate this course. And GIAN ton, which is gigaton of CO2 that was emitted to the environment. And this is actually a record high, and it's continuously increasing. Out of that, more than 90% is from the fossil fuel, and with the share of coal is about 40 to 45%. So this is the scale of the problem that which we are trying to address. What has been done so far and what is feasible? This problem is actually very difficult. It's not like I can do it tomorrow and install it and there is something sitting there. No, it's not, because this is a multifaceted problem. So first problem is, one is the cost of capture. So that's why we are all here. We are trying to lower the cost of the capture. You have seen all kind of numbers in the literature, and $50 per ton, $100 per ton, $200 per ton. For the direct air capture, more than $500 per ton, and all of those numbers we have seen. But we need to reduce it, because ultimately, who pays for that cost? It's the customer like us, right? The price of everything will go up. So that is one aspect. But the other thing is that what you do with the CO2 that is being captured, right? This is one of the biggest issues that which we have. Now, what has been done, and I have been actually, to be honest with you, I've been fortunate to be working with US Department of Energy for the last 15, 20 years. We have worked for about 10 national labs and more than 20 industries that are trying to commercialize the CO2 capture technologies. And I've seen actually massive amount of work going on in terms of understanding what happens to CO2 when you try to sequester it. Most of the model says that if you are storing it appropriate location, there is nothing to be afraid of. They will be underground for millions of years without any issues. So what is being done? Like in terms of enhanced oil recovery, I know in the United States, in the Gulf Coast, in the like Louisiana, Texas, Oklahoma, in those areas, massive amount of CO2 is being utilized for enhanced oil recovery. Right now, it's about 50 million tons of CO2 that is being pumped underground and no issue anywhere. Some for enhanced oil recovery, some for just natural sequestration purposes. And this is actually doing pretty good. A lot of work has been done. There is actually all over the world, if you consider everything, more than about 200 million tons of CO2 is either being captured or utilized. But compare that with this 34 billion ton. Like this looks like a peanut, but we are going there. So some states in the US I have seen is very progressive above others. So if you type on your phone anytime, California ISO, CA ISO, and you will see that any point of time, they track how much of the electricity is coming from renewable, how much from nuclear, how much from biomass, how much from natural gas. At any point of time, you will see about more than 50% coming from renewable energy. Their average last year was about 60% coming from the renewable energy. For the first time in the United States, the amount of power produced by the renewables exceeded that produced by the coal. There is threefold increase in the penetration of renewables in the grid. This problem is also multifaceted, as I said, that it's not like you put renewables. The problem there is that what happens if there is a cloud passing by the sun? You will have a dip, there are critical things, the power will go off. So you need things or management so that you are predicting when the cloud is going there. I have seen those mathematical models that actually keep predicting it. And if you go to California ISO website, they show you what was forecasted yesterday and what is right now. You will see they are very close. So you need a very advanced planning and a group of people always working very actively there. But what I wanted to say here is that a lot of work is going on all over the world right now. And if you see the G7 nations' emissions in 2023, right now their coal usage is at the 1900s level. And their CO2 emission is what it was at 1950s level. So there has been a lot of progress that has been made, but we have a lot of problem to solve. I'm really glad to see all the youngsters and our future leaders here. You will play a very big role here because, as I said, the problem is not one. There are many problems. There is a social acceptance problem. As I said, that if I say, okay, this is a global warming, I can put an air conditioner and run away from the problem and say, I'm good, right? This solves my problem, but it increases the problem for the entire world. I have also seen the statistics which are highly local and temporal. So this is also something which we have to keep in mind. So somebody might say, oh, last year in March, Vizag temperature was like this. To be honest with you, that really doesn't mean anything. Because what you have to really see, what is happening all over the world and how it is distributed locally. So one particular day in one city or one location does not mean that I get a clear idea about what is happening all over the world, right? So if you see the trend, there is actually really, it is going in an alarming state. We really do need to do something. We cannot sit on the outside of the fence and keep watching. So we need to be engaged, active, and that's why I will say that this particular workshop, that when Dr. Palla was actually first spoke with me, I was really glad that he had this thought here to organize this course here. I would like to share what I have come across, what I knew from starting from the fundamentals to the commercialization. I worked with multiple companies that are trying to commercialize the adsorption technologies. So please, let's interact with respect to that. I know those things are not included as part of the course, but we can actually have all this discussion on the side and answer some of the questions to the extent that I know. Finally, I would like to thank the IIPE management. I could clearly see this is a lot of progressive thought here with all the work, such a focused work. I have not seen as part of any institute there. As I said, that other than these industries and also the national labs, I'm fortunate with working with many top universities, including UT Austin, Carnegie Mellon, Georgia Tech, UC Berkeley, but I have not seen such a nice, focused goal towards achieving net zero and focusing on the energy. So looking forward to interacting with all of you, and once again, thanks for inviting me here and giving me the opportunity to talk and interact with all of you. Thanks.
So thank you, Professor Bhattacharya, for sharing your experience and such an insightful words. Now, we are equally privileged to have Professor Ravichandra Datta as our Indian course instructor. Dr. Datta is an assistant professor in the Department of Chemical Engineering at IIT Dharwad. He completed his PhD at the University of Queensland and pursued his postdoctoral research at the Max Planck Institute of Polymer Research, Germany, as well as the University of Queensland. His research focuses upon the gas separation membranes, AI-based material discovery, and designing energy storage materials. He has published numerous international research articles and delivered several talks. Sir, it is an honor to have you here. We welcome you to this stage to address the audience.
Thank you so much. Good morning, everyone. You can hear me, right? Good morning, everyone. So, uh, respected Professor Shalivahan, Director Sir, and Professor Vijay Kumar, Dean R&D, and Sri Rampal Dwivedi, and Professor Sridhar, so and all other members present here. So, good morning, everyone. So it's my pleasure to come here, especially after 15 years where I did my bachelor's in chemical engineering from Andhra University. So it's so hard to come in between the semester, especially when you are teaching in an IIT. And the fact that I'm coming back to Vizag is kind of like an emotion. So that's where I feel so happy to come back, and yeah, I'm happy to see you all, and then present whatever knowledge I have for some time. Before, because so many people kind of like talked about the importance of the problem and so on and so forth. So I will not get into everything, but I will just kind of like share a couple of things which we actually follow at IIT Dharwad. So whenever people say net zero, net zero, net zero, even I also think like I don't know when it will happen, whether it will really happen or not. Because when you see the big goals, we may not able to visualize all the time. So, but this happened, I think last year or sometime our directors are took the Department of Chemical Engineering people to the Tata Motors, which actually have a plant in Dharwad. So they actually kind of like have a plant which is kind of like have net zero in the plant itself. So it was like so inspiring, and then immediately our directors are kind of like said that I want net zero in IIT Dharwad by 2030. So that is the goal we have had, and then kind of like we are working towards everything. Even if you see like our cards, like visiting cards. So what our directors are did is like you kind of like printed visiting cards. On the back side he said like IIT Dharwad will be achieving net zero by 2030. So that's kind of like pressure we have to kind of like able to reach the goals. So that's one thing which I kind of like say that net zero is not at all impossible. We can make it if we work hard. So that's one thing. Second thing, I just want to highlight that especially India is expected to contribute 25% of energy demand in next 2 decades. So it's not only kind of like highlights the challenges ahead, but it also highlights the opportunities ahead. So when we kind of like went to Coal India last year, so they were saying that we have like a huge amount of coal reserves. So maybe useful for like next 100 years, 200 years in India. But our coal is full of ash. So when we burn this coal, it's a lot of CO2 will emit. So how can we kind of like reduce these things? And how we can kind of like develop materials in such a way that we are able to capture it, at least first capture it and then convert it. So especially this course is very much relevant to India, and especially when we kind of like highlights, like this course highlights the modeling and simulation aspects of the capturing CO2. Because we have a lot of computational resources across the India with the name of Param. So, right, either you call it Param Shive or Param Parag or whatever the name you call it, we have like huge amount of computational resources, and how we can make use of these computational resources to kind of like solve this challenge. So basically in this course I will be kind of like fundamentally focusing on teaching on fundamentals of adsorption, how we can kind of like use atomistic simulations or density functional theory calculations to understand the CO2 adsorption in different materials, and how we can actually screen and select the materials and so on and so forth. So I look forward to kind of like have fruitful discussions with you all. And thank you so much IIPE for giving me this opportunity and conducting this very much relevant course in Visakhapatnam. Thanks a lot.
So thank you, sir, for such of your words. Now I would request the director of IIP, Professor Shalivahan, to please come on stage for the felicitation of both of our guests. Professor Bhattacharya. Professor Bhattacharya, please come on the stage. Meena? Professor Ravichandra Datta, please come on stage. Now, to conclude this inaugural event, please kindly stand as we honor our national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
recording your face. Use the mode, that is also fine.
Okay.
So you got to get used to it initially. You can get the eraser. I think this is much easier.
With the mouse. Yeah. Maybe it.
We will manually control the camera if you are riding on the GoPro.
Just like how you have the NPTEL.
NPTEL.
Oh, okay, then it's easy.
Yeah. Sit and write for the tutorials are 3 hours. This is the arrangement for
I
software you need to move.
yeah, but the software I have to tomorrow.
Not more rapid.
No, yes.
Because they will give the jobs and
Which I will
if you
not
move
do.
here, this is fine. Here,
Yes.
don't go that side because
Uh,
completely.
that makes sense.
You can use this part.
Oh, it's not coming. Okay. Is there anything we need to do? No, it shows here. Okay, good.
So we're going to start the lecture 1.
Ready?
Start with interaction.
That would be good, actually. We can see this. And then later on, we'll talk about, generally, I prefer if there is a name of the participant, like they can write in a piece of paper, fold it and keep it in front of them. That way we can interact more closely during the workshop, which they can do later, actually, because the workshop starts from tomorrow.
Welcome everyone. Welcome to the lecture 1. Lecture 1 will be delivered by Professor Devanshu. So before going into the lecture, we would like to know about your background. We'll have one small interaction. So you can introduce about yourself, your name and where are you from, where are you working, and what are the areas you are working, and if you are expecting any specific topics from this course that you can mention. Okay, is this clear? Okay, can you start? Yeah, please.
Good morning, sir. Myself, Naman Kumar Aswali. I am working in Rashtriya Ispat Nigam Limited. I am Manager Operation Energy Management Department. So basically, as you must be knowing, that the iron sector is also a highly carbon intensive industry. So we also see the calculation part of CO2 emission pattern of production. So I am looking forward to learn new techniques that which we can help in our industry.
Very good. Thank you.
Good morning, sir. Good morning, everyone. Myself, Durga Pravina. I'm working as Senior Manager in Energy Management Department of R&D. And currently, sir, we have blast furnace gas and also the flue gas. So that has got higher percentage of carbon dioxide emissions. So we are also looking for areas where we can reduce these carbon dioxide.
Very good. Thank you. Switch over. We go this way. Yeah.
Good morning, sir. I'm Atli from CSI NIST, Trivandrum, Kerala. Currently, we are working on one of the project to capture the CO2 from high temperature. So we are working on high temperature materials, mainly on steel plants, focusing on from blast furnace, flue gas, and service gas.
Very good. Thanks.
Good morning, everyone. Myself Achu. I'm a senior research fellow at CSIR NIST. We three are from NIST Trivandrum. So we are basically working on intermediate to high temperature carbon dioxide capture. We are in the material development part. So through this course, we are hoping to get insights into the modeling part so that we can go further into the scale up and implementation.
Okay. Very good. Thanks.
Good morning, everyone. My name is Dr. Prince George.
So please be loud, okay? Because
I'm from CSIR NIST as a senior project associate at CSIR NIST. So we are actually working on the CCOS capture mission. In that, we are actually looking for CO2 capture from point sources, especially from steel industries.
Okay.
So that's actually our aim. So we are actually having our material development. So we are planning for the process simulation part. So how to improve like that, process modeling.
Very good. Thank you.
Good morning, everyone. I am Swapnil Divekar from Indian Institute of Petroleum, Dehradun. My basically research area is development of adsorbent and adsorption-based separation technologies. CO2 capture is one of the areas that I work. From this particular course, sir, my expectation is to get into topics like use of Aspen adsorption along with the membrane technologies for development of hybrid technologies, just to get the initial idea of it. And I'm very pleased to be here. Thank you so much.
Okay. Thank you.
Yeah, good morning, everyone. My name is Mausam Banerjee. So basically, I'm from the industry only. Means actually, we have founded our own organization, which is particularly dedicated in its carbon capture and utilization. I'm having almost 15 years of experience in the renewable energy sector. I have worked for multiple private equity companies and so. So as a opportunity in the industrial sector, we have started this organization approximately 7-8 months back. We are trying to implement this carbon capture and utilization project for the multiple industries, especially for the hard-to-abate sectors such as fertilizer, steel, transportation. Not only we are looking for the solution for this carbon capture, we are also looking for solution for the utilization. Means utilization, since government of India is coming up with multiple scheme where India also wanted trying to become energy independent. So we are also trying to develop some of the solution where we will be capturing that CO2. Along with that green hydrogen, we will be producing this synthetic fuel, SAF, ethanol, methanol, which is having some commercial value at the industry level.
Very good.
Thank you. Means happy to be here, trying to understand all the theories and so.
Sure. Thanks.
Good morning, sir. Myself, Selva Balasubramanian. I have done my PhD in material science engineering on the aspect of developing metal organic frameworks for chemical detoxification. Actually, I'm new into the field. Now I want a transformation towards CO2 capture and hydrogen storage, sir. That's my.
Yep.
Thank you.
Good morning all. Myself K. Kishore Ramnan. I'm a full-time PhD scholar in Sastra Deemed University. I'm working under the guidance of Dr. Gautam B. Jagdishan sir. My research is focused on synthesis of metal organic framework for the removal and recovery of heavy metals, specifically uranium and thorium from water sources.
Right. Thanks.
Thank you.
Good morning, everyone. I am Dr. Abhimanyu Kar. I'm from Assam Energy Institute, which is a center of Rajiv Gandhi Institute of Petroleum Technology, RGIPT. And I teach mechanical engineering here. So this is a new field for me, but I like the topic, and I thought since I have been teaching courses like renewable energy to undergraduate students, and I have done some work in other fields of renewable energy, so it will be great to learn this new topic. So probably I can do some work in this topic in the future.
Very good. Thanks.
Good morning, everyone. My name is Meenu Kumari. I am from IIP, Indian Institute of Petroleum and Energy. I'm doing PhD. My topic is the characterization and theoretical investigation of porous material. So from this, this course is related to my topic. So I can learn so many things from this.
Yeah. Thank you.
So good morning everyone, my name is Iradat Hussain and I'm a second year PhD scholar under the supervision of Dr. Sridhar Palla, and I'm working on the carbon capture with the help of metal organic frameworks, and I'm trying to do theoretical modeling as well as experimental investigation. Thank you.
Thank you.
Good morning everyone. I am Dr. Priyanka. I came from CSIR ISCT. I am working as RA under the guidance of Dr. Gangagni Rao sir. So we are a team of 5 members. So we are working on biogas purification experimentally. Here we came to understand the modeling aspects of adsorption techniques. Thank you.
Yeah, thanks.
Good morning everyone. I am Dr. Abhilasha Rai. I am also under the Gangagni Rao sirs. My major work is the CO2 capture, biogas purification using the microalgae. My background is biotechnology. So microalgae, and I know the any CO2 concentration, higher concentration for biological, it will be toxic. So if we'll go with the hybrid technology, adsorption plus absorption, it will help. So for that, I am here.
Right.
Thank you.
Thanks.
Good morning everyone. I am Pavitra Bharati. I'm a chemical engineer. So now I'm working as a project associate in CSIR IICT. So my project is also based on biogas purification and CO2 adsorption. So I felt it will be useful for me.
Very good. Thank you.
Good morning, everyone. My name is Yamni. I am related to biotechnology. I am working as a project associate under A.G. Rao sir from ISCT. My project is related to biogas purification and CO2 absorption, so it will be useful for me. Thank you.
Thank you.
Good morning, sir, and good morning to all. My name is Sri Krishna Mupuri. I'm currently pursuing Master of Technology at Andhra University. I want to explore and leverage the knowledge in this sector, so that's why I'm applying.
Okay.
Thank you, sir.
Good morning, everyone present here. I am Diptangshu Vishwas. I am studying in Jadavpur University, Kolkata, under Professor Ujjani Sarkar, and my field of work is under carbon monoxide capture, and under that CO2 interference is a major issue, so I am here for the course.
Oh, very good, thanks.
Good morning to all of you. My name is Dr. Arshdeep. I am working at Haskej as a senior scientist, which is one of the startups incubated at IIT Ropar. I am a recent graduate of IISc Bangalore with a PhD on multi-component gas separation. So I'm here just to get more insights into modeling and simulation aspects. Thank you so much.
Very good. Thank you.
Yeah, so good morning everyone. Myself Praful Jha. I'm a project associate working under the supervision of Dr. S. Venkat Mohan sir at CSIR IICT. So basically I'm project associate in a project related to biopolymer production. However, my lab is very actively involved in this CO2 capture and mostly in the gas and electro fermentation things. So I want to learn more about this Aspen software and all.
All right.
Thanks.
Thank you.
Good morning to all. My name is Mansi Chandawat. I am working as a project associate in CSIR NEERI Nagpur under the project National Implementation Plan on Persistent Organic Pollutants. So from this course, I am expecting to learn more about the CO2 capture. Thank you.
Go from there. I think the back.
They are not.
Okay, not anybody. So the online participants,
They can hear, right? Online participants.
they can unmute themselves or?
So the online participants, you can unmute and introduce yourself.
That will also confirm that they can hear us, which is.
They can hear us. The person sitting there, right?
Yeah.
Is
Right.
on now.
Right. Yeah, this would be.
If possible, yeah, switch on your video also so that we can see. Now, these are the people on.
Right. Because they need to ask us questions, right? It maybe they're not able to.
So they can unmute themselves, right? So online participants, please unmute yourself and introduce. Can you confirm that you can listen to us?
Just ask them to put it in the chat actually, if
Yeah,
they cannot
yeah.
hear us, because they cannot confirm, right?
So if you cannot unmute yourself, please drop a message in the chat box.
They probably cannot. Those who are online, can you hear us, please? One of us, if you can hear us, just put a message there on the chat. This one is on, right? I don't think we can. Yes, sir, you are audible. Okay.
Yeah, Rakshit, can you unmute yourself and introduce?
Hello, Rakshit. Oh, this one is. We'll just see. Oh, he said he doesn't have mic in his PC.
So we'll do one thing.
Probably.
We'll start the lecture.
Yeah.
And we'll do the interaction then.
They can hear us, right? That's the main thing. Okay, so let's start then. No, not he's saying not arrange, not yet. Like one of them, Santosh said not yet.
But we'll figure it out. We'll start
Okay.
the lecture.
Okay, perhaps during the lunch time.
I will send a message to them to have 5 minutes of introduction.
Yes, and because what I wanted him that actually they can hear us. But one of them, yeah. Yeah, probably we're getting delayed maybe, right? So. All right, so we are good to go. Okay, so I just wanted to confirm that those at the back, you can hear me. One of you can please confirm. Can you hear me? Just raise your hand if you can hear me. Okay, all right. So I will be loud so that you can hear me, right? So, but if you don't, just let me know, because the air, I just cannot figure it out how much loud I am sometimes. So please. The other thing is that feel free to stop me at any point of time if you have any question at any point of time, because the idea of this thing is not like a lecture. We would like it to be more interactive over the next 5 days, okay? So first thing is, okay, so wanted to give you an introduction, and I already said during the previous meeting, previous presentation, previous discussion, that where we are, what's the scale of it. So if you see the energy-related CO2 emission, this is actually increased by 1.1%. This, you are seeing this, all the numbers I'm giving for 2023, because 2024 numbers are yet to be confirmed. So like a lot of these numbers are coming up. So we'll be getting those things, numbers correctly, but 2023 numbers are all confirmed. So this actually increased by 410 million ton, and this is the new record in 2023 that which we had. And if you look into it, in 2022, the increase was about 490 million ton. So it's not that much different in 2022 versus 2023. And the other thing is that if you look into the coal, it actually contributed to this 65% increase. So this is one of the big things that who is the main contributor, so we identify that. The other thing is that if you look into that, how much of these is basically coming from burning of fossil fuels, you can see that out of this 37.4, about 34 billion ton is coming from burning the fossil fuel. The rest of the CO2 is actually coming from a lot of other sources, like for example, chemical production. If you see in the lot of the petroleum and the petrochemical processes where the CO2 is getting produced and those are getting emitted into the sources, there are other sources also that is also produces CO2, including a lot of animals and other sources too. So those are not really much. Most of it is coming from burning the fossil fuel. If you notice here that 45% of that is coming from the coal, 35% from oil, and 20% from gas. Once again, it says that majority of that is coming from coal. Now, if we compare this with respect to how the advanced economy is actually doing, like these are mainly the G7 countries, their GDP grew by 1.7%, but emissions fell 4.5%. And this is a record decline. There are actually a lot of incentives, as I will discuss. Many governments actually came up with a lot of incentives. Like as we were discussing today, Government of India is coming up with a lot of incentives as well. So because of all of those, there is a lot of declining in the emissions coming. So for these countries, this has decreased by 520 million ton, and this is now back to their level 50 years back. So this is really a great news. So that tells you it is possible. It's not a problem that we cannot solve. It requires a lot of government incentives and the works and the focused work, but with that, it is possible for us to go there. If you look into it, like as I said, the coal was actually one of the main contributors. So now if you look into some of these countries here, their coal demand is actually at the 1900th level. So that basically means that it's very low right now, and that's one of the main contributors there. Now, if we look into some of the Asian countries, now the statistics is not available for all countries. So I know that this organization, IEA, is one of the organizations. So look into this link here. It will keep updating every year so that you get the numbers, because I wanted to, they actually track the CO2 emission all over the world. It's not necessarily very well documented for all countries, but some of the countries it is well documented. So it's observed that the China actually went up by 565 million ton in 2023. This is by far the largest increase globally. Also, the per capita emissions in China are now 15% higher than any advanced economies. In India, the emissions during 2023 went up by 190 million ton. And it also said that there was a weak monsoon, increased demand for electricity, and that also cut the hydro production. So those are the contributors for the CO2 emission here. But I would say the per capita emission in India is still remain very low compared to the global averages that are. So that's because of our lot of populations and lack of energy demand that our emissions still remains low. But a lot of the emissions in India is because of the coal. And that is something that I'm sure that is being looking into there. Now, what is happening in terms of the CCUS? There are about 45 commercial entities that are operating all over the world. When I say commercial entities, these are not pilot plants. This means that these are commercial plants which are capturing CO2, and they are either utilizing the CO2 or they are storing it, right, underground storage. So it is basically all of those. There are 45 of them there. And these facilities captures about 50 million tons CO2 annually. This is a big one, but I wanted to give you some examples of some of these projects here. This place got cut down, but I'll read it for you here. So a couple of example plants like what they are doing right now. So let's focus on that. So this one, the Blue Flint ethanol project. This is actually storing about 600 metric tons of CO2 per day, underground about 1 mile below the surface in one of the formation in North Dakota, USA. So this is basically the ethanol production. As you know, that there is a lot of, from the fermentation process, it produces CO2. So they are capturing the CO2 and they are putting it under the ground. And North Dakota has a pipeline for CO2 for quite some time. They have already pumped about many million metric tons underground. They are monitoring all of those capture plants there on a regular basis. This is another one these are all that actually started in 2023. So these are some of the plants, but I'm not talking about the other ones. These are the ones that started operating in 2023. The Lindy Clear Lake Capture Facility, this is in Texas there. And what they do is that they supply CO2 and hydrogen to a Celanese plant that is converting that to producing methanol, actually. So Celanese, as you probably know, that they are one of the companies who are working in the green methanol production. So this is also another usage that people are using. Heirloom and the Global Thermostat, they have now 1,000 tons CO2 per year DAC facility and in the United States. And then there are also 4 projects in China that actually started here. In the Petronova plant that has actually operating for quite some time, but it got shut down because of other maintenance and other work that they had to do here. These guys are actually capturing about 1.4 million ton of CO2 per year. This is outside of Texas also. They are using it for enhanced oil recovery. So this sends it about 130 kilometer there. And as you will see that for my discussion, other thing which I will keep discussing about the CO2 transport, which is one of the very critical aspects that we need to consider, CO2 transport. So what it basically tells that this is possible and this is happening in many parts of the world there. Any questions so far from any of you? This is mainly statistics. I put all the websites here. and these numbers keep updating and all that stuff. So you can look into that going forward. Now, where we are, like you all know about the Paris Agreement, right? We are really, really behind. Many countries committed, but there is not steel on the ground. The point is that it's not, the commitment does not help unless you put the steel on the ground and do something about it. Okay, that's a lot of things trailing down. Now there are about, currently this is the good news, is there are about 700 projects in various stages all over the world that are actually trying to capture CO2 or trying to utilize the CO2. One of the big things that is coming here is that in terms of the value proposition, the problem is with the CO2 is that you capture CO2. There is no issue in terms of capturing CO2 and putting it underground. That can be done. No issue there, actually. The problem is, as I was saying, it's one of the cost. Second is, what is the value proposition? Like, how do you get the money back, right? Now, that's why a lot of work going on in terms of the CO2 utilization, in terms of, as I was showing, that enhanced oil recovery. Like one of the earliest plant you probably know is actually in Canada in the Boundary Dam. And I have visited that plant actually, where it's about 400 megawatt power plant. They capture CO2 and put it for the Canadian oil sand recovery, right? And those guys are actually monitoring those spaces for many years. And sometimes actually this can be seen through the propagation of the seismic wave. So on the other side of Canada, that place is actually Japan. So they're actually from that side, from the earthquake, they actually monitor that if there is any CO2 getting penetrated through the ground and going other side. In fact, actually, if you have a seismic wave, if you have a CO2, that actually let you propagate it. So Japanese researchers, they were actually always monitoring that site where they are actually storing CO2. But those places actually very securely storing CO2 for many, many, many years now, actually. So it is possible, it is happening, but we have to think about some value proposition here that everybody is trying to work towards. The other thing I would like to say here is that there is about 35% increase in the announced capture capacity to be realized by 2023, and the storage capacity is 70%. A lot of places where the storage is being taking place, I am not really sure about India, and I'm sure many of you may actually inform me and are well aware of it. But in the United States, I know that for the entire country, they have a map now where the CO2 can be located. All the natural formation in the countries has been mapped. Every state, every locations that where you can securely store CO2 there. So if there is a local capture, you can store under the ground, and those are secured. Of course, there is monitoring and other things, but this has been mapped by the geological survey groups, actually. So that's why there are announced storage capacity rose by 70% here, and that is what I said that by 2030, that should be captured when will go up by 435 million ton per year, and then 615 million ton CO2 for storage. This will go up there. However, these are positive, but we are still about 40% and 60% with respect to the captured and stored with respect to net zero emission level. Based on also all these propositions and based on what is expected in terms of the renewable penetration. As a researcher, and I see all your diverse background, the other thing you have to keep in mind is that when you actually try to do all of these and think about bringing the renewables, when you start going beyond 50%, it can be a troublemaker. The problem, as I was saying, that if you have a wind energy and wind suddenly falls, and as they always claim that whenever you needed it, you don't get it. Right? That's the problem. You have a wind, you have the solar. On a summer day, you need, I need energy because everybody is cranking up their AC, but that's the time you will not get it. What do you do at that time, right? So if you are shutting down these plants and you go to renewables, you have to have a backup plan, what do you do with it. So bringing in 100% renewable is not the solution. What do you do during the night time? Can you store that much of energy? It's still a lot of these open questions come there. So a lot of other angle that is coming. I'm probably diverting, so I'll not go in that area. But let's see what we see here as per their IEA projection. So by 2030, this is the gap, and then notice this part here. This is basically a lot of these things we are expecting to really be how much of these will be operating, what is under construction, what is under advanced development and concept and feasibility, right? So if you notice this part, this is not really increasing by that much. And as you always fondly say, there is something called a valley of death, right? They always say that there is about only 5 to 10% of the project can cross the valley of death. So you get the project, wonderful, wonderful, wonderful. At one point of time, your business proposition goes down, you make loss, or some other problem shows up which you do not anticipate in the lab scale. When you start doing piloting it, you start realizing these issues, commercialization, and that gets value of death. This number I said, this number is kind of from US Department of Energy. They basically say generally their experience is it's only 5 to 10% of the project will cross the valley of death. Okay, so a lot of projects we need so that we can have a large number of projects that can cross the valley of death. This is the reality because we don't anticipate from lab scale analysis what will be the problem. So I'll be switching gear after this, but let me know as of now, anybody has any question, any perspective or any thought, please. Yes?
Yeah, it's a question plus perspective. So as of now, the slides that we have shown, sir, most of the carbon capture that is happening is mainly for the oil industry in terms of enhanced oil field. So just trying to understand from the global perspective, especially for the Western countries, means what's the plan for the conversion? Means until and until the conversion technology is well developed and commercially applicable, the commercial numbers will not match. All this enhanced oil recovery, it was mainly done by the oil companies, Occidental, Nova Petra is there. So to have a large scale implementation in hard to abate sector segments, so it's very much important to have that utilization factor coming. Utilization factor not only for the enhanced oil recovery, for say it might be permanent storage of CO2 in form of say building material or maybe synthetic oil and so, or maybe other products replacing the existing say fossil fuel based petroleum with this kind of a net zero kind of a petroleum. So just trying to understand how it's been going. And another perspective is this, in terms of government of India, actually government of India has come up with a policy, though that policy is currently in the draft stage. Bureau of Energy Efficiency has come up, carbon capture trading scheme that will be implemented from 2026. Unfortunately, means as a commercial person, I do feel that carbon capture is not included in that. But in that, government has included green hydrogen production from biomass or bio-CNG. Another, there is a clause called alternate fuel. So based on Indian scenario, we might use in that way so that there will be commercial value for carbon capture and utilization.
Yeah, very good. Thanks for that comment. So those who are online, I'm not sure you could hear or everything. They could? Okay, so those who are online, the question was that what about the CO2 is being used right now mainly for enhanced oil recovery. So what about other usage of CO2, the CO2 utilizations? And there was some perspective about some of the government of India policy in terms of mainly focusing on the green hydrogen, but not necessarily for the CO2. What I would like to say here is that because the massive amount of CO2 that is getting generated, you think about CO2 utilization, any market, carbon market that you think about right now, it will be saturated. So if you think about urea production, you think about methanol or ethanol production, carbonate productions, or there are a bunch of other chemicals, thinking about the formic acid and others, any of those markets based on their current demand, they will be saturated. So the idea here is that some of those can be going to the value addition, but some of them actually has to be stored only under geological sequestration, which is not adding value, but it is mainly for the storage purposes. Like what I was saying was about that methanol production plant, and they are getting it from fermentation process, but that entire CO2 is getting underground. So they are storing it. So they are making money by selling ethanol there, but this is coming from there. The other thing which I will be discussing in a moment, that this comes from another perspective. So the question is, can the storage of CO2, can I make money by storing CO2? Yes, you can. I'll come to that in a moment. Yeah, so I know that green hydrogen production does not come on its own. There is a CO2 footprint. So you have to do the life cycle analysis really to understand that what is the CO2 footprint of that. So the issue is this massive amount of the CO2. Can I have the demand of carbon products equivalent to the 34 billion ton CO2 equivalent? No, we don't. Any market you think you will saturate it. So this goes to my next thing here, is that this was a very timely question, because my main thing is that what the government can do as part of an incentive to make this capture possible. So one thing that was done in the 2022, the Inflation Reduction Act, they did this 45Q tax credit, which gives you $60 per ton of CO2 used. So if you have 60, that basically means that if you're able to capture CO2, say, by $40 per ton or $30 per ton, then this can actually, you can make money by doing this. But now you say, well, my technology will take you $200 per ton. You cannot. So this is a competitive market, definitely, but this is a government incentive. And a lot of those projects that I was saying in 2023, they were actually making money because of this, because the government said this incentive. So that's one thing. The other thing that was done was the clean fuels and product short, which is basically like producing fuels and chemicals that through CO2 utilization, that also give you that much incentive there. Like for example, if you're producing ethanol there, but you are getting the CO2 released to the environment versus you say, this CO2 I'm utilizing somewhere, or the CO2 is being captured from another plant and I'm converting this to a fuel, you get these as a clean fuels and products incentive. So this is all depends on the lot of government support that will be needed, at least for now, to make these projects off the ground. The other thing is that European unions also came up with a lot of these incentive. One of these is this Refuel EU Aviation proposal, and that actually synthetic fuel for aviation, that was really targeting about that. Many of you know about the SAF incentive all over the world that is going there, and then how much to be increased slowly. Then Canada also, they had a lot of proposition there and how much they will be funding. So one thing which I would like to say is that as of today, you go to somebody and say, do the calculation for me, do the economics for me, and somebody will say, hey, yeah, you know, your technology will cost you $100 per ton. This is not the calculation for nth of a kind. You are doing the calculation the first of a kind. That basically means is you are saying, this is my first plant I'm building. But remember, like when these plants are built, like thousands of those, and you are doing the mass scale production of the adsorbents, solvents, or other technologies, the cost will actually go down. You have to go there. Like Ajay was saying, the renewable energy, that big penetration that you see right now in the United States, lot of those was because of the incentive that was taken during the Obama administration there, when the government actually gave lot of discounts. So I'll say, okay, I'll give you 50% discount, you buy solar. So what it actually helped is that a lot of people actually started buying it. Like in my household, I can put a solar and I can sell it to the grid. I can make money actually. But I cannot make money in the first year, second year, because I have to make massive capital investment. But if the government comes and says, I will give you 50% for this one, So do not worry. Then also take tax credit. So I'll give you tax exemption and all of that. Then once I buy it, then my capital expense is done. Then I am contributing to the market. So a lot of roles and incentives from the governments are actually needed for reducing the cost. It's almost like a chicken and egg problem, that if you do not get it off the ground, you will not be able to reduce the cost. And if you cannot reduce the cost, you cannot get it off the ground, right? You see, this is a difficult problem actually to solve. Okay, so I'm changing the gear. Any other comment, questions, anybody?
Sir, I would like to add another point. So regarding the previous slide, regarding that previous slide, so this RFU EU aviation proposal, it has also a unique point. It defines that by 2041,
yeah,
the CO2 source should be biogenic source.
Yeah.
So it's also what many of the organizations are doing. They are burning coal
Right.
or any fossil fuel, then they are capturing that carbon.
Yeah.
But the EU regulation says by 2041, all the source of carbon should be biogenic.
Right. Right.
So it's also a challenging aspect in that.
In many countries, yeah, that is true. Absolutely, I agree. Yeah, that is challenging for many countries. I do know, like again, I have a project on that SAF, and working with some of the companies. I do know that especially in the US, that's a market I most well aware of. There are a lot of energy crops. These are short rotational crops that basically these plants actually grow in 3 to 5 years. This actually grows like 30-meter tall. And so you then actually utilize them. A lot of research has been done. So basically these are, they know as the energy crops. They rapidly grow, and then you can actually convert them to fuel, and then you go to next rotational crops actually. These are short rotational crops.
Sir, actually, Tata Steel did a project approximately 2 years back in Jamshedpur plant. So, since the regulation was not clear at that time, actually the carbon that they are absorbing, initially they planned to use that CO2 for the production of green methanol. But later on, they came to know, since the source of the carbon is coal, they will not be getting that green methanol tank.
Right.
So, as a result, that project was dropped.
Right. Yeah. Yeah. Makes sense. Yeah. Absolutely. So we'll move on. So in terms of CO2 capture technologies, where do we sit here? If we look into here, we have the adsorption, cryogenic, and membrane. All of these technologies over here. And adsorption, we have chemical and physical. This is a very important category here as well. Membrane is also a very important category here. And we will be focusing on the adsorption here. Many different type of adsorbent are yes. Many different types of adsorbents are being actually considered there. But I just wanted to say that this is one of the many technologies that are being considered there. Hybridizing these technologies makes sense, and I'll be discussing some of those. So what is adsorption? This is just to give you, many of you are not from this background, so I just wanted to say, basically, this can happen for gas, solid, liquid, solid, and those type of systems. For water purification also, it is used quite often here. So some solute will be sticking to the surface. When we say stick to the surface, that does not really mean the sticking, that basically meaning some kind of a weak bond or a strong bond formation there, which we call the adsorbent, right? And then what we need to do is that we adsorb it from the gas or the liquid, and then we need to desorb it. So it goes by a cycle: adsorption, desorption, adsorption, desorption. When we say the rate of adsorption and desorption become the same, we say the system has reached equilibrium. And this happens due to the surface energetics. And I'll be discussing some of the thermodynamic aspects perhaps day after tomorrow's lecture, actually. Okay. So the first thing is that delta G is negative for adsorption. So this is actually spontaneous, right? That's what this thing, something which you need to know here. Adsorption is exothermic, so we know by our convention of sign delta H is negative. You cannot just take it at the face of it. This is one of the biggest thing here, and as you will be discussing here, this delta H actually impacts lot of things. So you can have one of the greatest adsorbents, but if this delta H is very high, energetically it's not favored. Okay, so that is something which you really need to consider here. Now, types of adsorption will depend upon how these molecules interacts with the adsorbent and also among themselves. Okay, so I will discuss this from the perspective of there are three main types: physisorption, chemisorption, and physicochemical adsorption. So physisorption is basically where, if just by the name of it, right, it's a physical adsorption mainly due to the weak van der Waals force, and then when we have the chemisorption, then it forms a chemical bond, right? And that basically means is that there is one type of a material, like mainly amine type of a material. This is impregnated or immobilized in the solid. So many of you, as you are working in the, like you were talking about metal organic framework, that metal organic framework can capture through physisorption. You can also immobilize some kind of an amine there to have it as a functionalized there. So it can both do chemisorption and physisorption, and we have actually a couple of papers on a metal organic framework which was impregnated with a diamine appended and tetraamine appended metal appended MOF, and it shows very peculiar properties in terms of the isotherm and the nonlinearities, and I will show you some of those results later on, that saying that it can actually lead to a very, very complex mechanism that is difficult to capture through modeling. But it can be, both of them can take place together. So these are not exclusive. So the confusion always comes like, okay, so physicochemical is where both of them are taking place. Like I was saying, metal organic framework, when functionalized, will do both of them, okay? Now, if we consider both of them, what are the differences? So if you look into the bond, like physisorption, is these are weak and the long range form that forms here. Chemisorptions are strong and the short range bond that gets from here. Look into this number here. This enthalpy is 5 to 50. Most cases, this will be like 10 to 15 or 20 kilojoule per mole. This guy can be very high actually. Like generally, as you know, like if you have an monoethanol amine, it will have about 90 to 100, mostly take about 95, give or take plus minus 5 kilojoule per mole is the heat of absorption in the solvent. If you immobilize it, this heat of absorption becomes very complex. It's very difficult to say what that value should be, right, predicting it. But these are generally high. So like those diamine and tetraamine appended MOF that I was saying, this has got a value of 65 to 90 kilojoule over mole. So you will be seeing that I will be discussing these very often. This is a take-home message for you. This is a number that you need to look into, this heat of absorption, why this is good and this is bad, right? So this thing actually hurts you in both ways. So when you are doing in adsorption, this heat will get released and it will heat up. If you heat up from an equilibrium perspective, then if you look into the adsorption isotherm, your equilibrium will go down. So you cannot capture as much. And then when you are trying to desorb, you will need this much of energy to provide to get it off. So it hurts you both ways. Unfortunately, some of the excellent adsorbents, which actually has got really nice adsorption isotherm, very high loading and all of that, has got chemisorption properties. And that's how they become very specific. But they have got both sides you need to weigh to find out what you should really go for. The other thing is the selectivity. This can be low selectivity and and this could be pretty high actually. So it could be very selective because of the chemisorption. And that is why you know the monoethanol amine, diethanol amine, all of those amines are still so favorite. Energetically, they are not good, but the thing is, they are so specific. They will only capture certain components there. So that's why even with those energetics, people love it. I will discuss what is the problem that if it captures something else. Now, sensitivity of adsorption to pressure, this is also another thing that you need to consider, especially if you are thinking about a membrane, especially if you are looking into the steel plant capture. Those which has got a very high CO2, you can take advantage of that high partial pressure of CO2, but this really helps the physisorption. Chemisorption can be largely insensitive. Monoethanol amine can capture 99.99% CO2, no problem. It will capture. These are so much like it because captures is through chemical reaction. But for physisorption, you cannot capture it. So that is also important thing here. Sensitivity of adsorption to temperature, this will decrease, and I know Dr. Pala will be discussing this adsorption isotherm, and you will see how those things behave. You will see that this will actually keep decreasing. Chemisorption, very complex, very, very complex, because there is one chemical part, one physical part. Physical part is Hertz, but chemical part is very difficult to say actually. It goes both ways actually. Now, one question comes is that if you're in the market and you are a business and you say, yeah, I'm actually evaluating like 5 vendors, or I'm trying to develop 5 technologies, which one is the best? There is not one good answer. You have to analyze it. So what are the things you need to look into? First thing is that it depends on the partial pressure of CO2 at the inlet of the capture unit. This is very different when you are thinking about post-combustion capture from a coal plant, 10 to 11% CO2 partial pressure. You are thinking about natural gas combined cycle, 4 to 5%, versus you are thinking about the cement plant, versus you are thinking about the steel plant, the blast furnace gases. Everywhere the partial pressure of CO2 is different. So this is the suitable technology depends on your partial pressure of CO2, one of the criteria. Other criteria is what is the percentage capture you are desiring. If you say, I want to capture 90% from a blast furnace versus you say, I want to do 99% from a natural gas combined cycle plant, it's a completely different ballgame. Your partial pressure of CO2 is really nothing. It's like 0.0001 bar for the natural gas combined cycle case. So there you need a completely different technology. That's why the hybridizing the technology can actually help, like membrane with sorbent or solvent with the sorbent, and those type of things can do actually a lot of good work there. The other thing is that what are you going to do with that captured CO2? If you're saying that this CO2 I'm going to putting it underground, it's a different requirement. If you say this CO2 I want to use for enhanced oil recovery, it has a different requirements, because like for example, there is a strict oxygen requirement if you are putting it for enhanced oil recovery, because you have this oxygen going there and it can create explosive mixture there. So you are not allowed to do that. But if you're putting it for geological sequestration, it is okay to do that. Then other thing is, like I do know that at Iceland and Microsoft bought that direct air capture, that green tag actually for that Iceland based CO2 capture unit, that is being used in a nearby Coca-Cola plant for the CO2. That's a direct air capture. You capture from air and then they use their geological energy for regeneration and all of that, and then put it to a Coca-Cola bottling plant nearby, right? That's a completely different CO2 requirement because it's a food grade CO2 requirement. It's a 99.999% purity of CO2. So you have to understand what is where is I'm trying to going to utilize it, or I'm trying to produce formic acid, I'm producing methanol or whatever. So that is another important thing. And also what contaminants you have in the incoming gas. Like blast furnace gas has got all kind of things there present here. Coal gas has got all kind of things here. Natural gas combined cycle, very nice, like in terms of contaminant, not so much. So all those contaminants, you must take those into consideration. Yeah, this I kind of already mentioned that for this. Like for example, if you're thinking about NGCC plant, and if you're doing 90% capture, partial pressure at the outlet is 0.00 bar, and then from 99 point capture, it enters the direct air capture range, right? If you compare it for the PC plant, with 90% capture, it is 0.01 bar. So see the comparison over here. And beyond like 99.6% capture, then we'll capture the DAC range, right? That is what it is. Compare this to the cement clean off gas, which has got about 30% CO2. It's very different ball game actually. So the adsorbent technologies will be very different. So it's not easy to give you one answer for this one. Okay, the other thing is why we care so much for that adsorbent. So the point you will be, and over the next 5 days we will be discussing this, but the equilibrium and kinetic properties of these adsorbents greatly differ at this PCO2, low PCO2. Some of the adsorbents are pretty forgiving for low partial pressure of CO2. These will still go to a very high loading. Some of them are highly sensitive. So you have to think that one. Other aspect is the kinetics. That is one more important thing. Equilibrium tells you one side of the story, but kinetic gives you the true picture, how much of close to the equilibrium can in reality you can capture. So if you're doing it in a lab scale and you say my equilibrium loading is so much, in reality, you may not even be able to capture 10%, go close to the 10% because of the kinetic limitation. You do not have the eternity just like what we do in the lab. Like in a lab, you can wait for 5 days, and a graduate student running a lab, no, not hurting the graduate students, but saying that they figure out what is the equilibrium, you wait for 5 days and say, this is the best data I could find, right? You are happy about it. But reality is that in an actual capture plant, this gas will be there for a couple of seconds. What is the close to the equilibrium you can go to? Because we are talking about a massive amount of CO2 flowing through the system. Your residence time is very low. If you say, I want a 5 days of residence time, the adsorbent bed will be the length of India actually, right? So it's not acceptable. So that's the other part you must take into consideration. The other thing is that if you have only considered physisorption, and if you want to go for a high CO2 capture percentage and you have a low concentration, it can be very difficult to go do that by physisorption. This can be advantageous for chemisorption because they are largely insensitive to partial pressure of CO2, but the point is about the energetics. So as I mentioned there and discussed, this chemisorption has got a very high heat, so it hurts you both ways. So you see, there is not a one solution here. Like this is nature, right? There is no, we always say there is no free lunch theorem, right? Like there is no free lunch. You get one advantage, there is a disadvantage. So you have to weigh the advantages and the disadvantages. This is one of the thing there that physisorption helps because of the low energetics, but you cannot achieve those high capture percentages. And chemisorption is the other way around, okay? Now, other aspects you have to remember is that when you think about the chemisorption, you can lose the chemical that is immobilized there. This can happen over time. So they could have a stricter operating conditions. Like you might say, temperature must be below 110 degrees centigrade or whatever, or the moisture content should be below some values there. These constraints may or may not exist for the physisorption. So this is other aspect you have to take into consideration. Constraint with respect to the operating condition. Another thing is the contaminants that are present, what happens. You might actually think about, why do I care if I have a contaminant present and I co-capture with CO2? So I can co-capture nitrogen and CO2 together. What is the problem? And I can put it under the ground. But what you have to remember there is that that nitrogen that you captured, you are compressing that nitrogen also along with CO2. So under what conditions CO2 is stored, if you're trying to think about storing there? It's more than 150 bar. It's stored under supercritical condition. That's where it is stable conditions. You put it through the pipeline more than 150 bar. So you are taking that extra nitrogen that you capture, like 5% nitrogen, put it through this, and then 150 bar you are compressing. That will actually take your energetics very go down, because nobody will give you credit for that much of nitrogen, and it's there. There are other things like sulfur is one of the nastiest stuff, because they will do the corrosion of the pipelines. Moisture content, they are also very bad, because when you go for the supercritical condition, that moisture will form hydrates. And that's one of the other aspects that we have to take into consideration. So contaminants is one of the big issues that you need to consider there. Other thing is the absorbents undergoing chemisorption and generally costlier than undergoing physisorption. And the other aspect that which you may not or should not forget, and this is something which I learned, to be honest with you, by interacting with the industry, is scaling up. So I can produce a absorbent in the lab scale. I am a chemist, I am doing it, I just produce a couple of grams. If somebody comes to me and say, you know what, for CO2 capture requirement in India, I need 1,000,000 tons of this material. Can I produce? Maybe I do not have that much of material on earth, the raw material that I need there. That's other aspect that which you have to remember here, is that scaling up the solvent of the absorbent to the scale that we need can be challenging. Okay. So capital expense and commercial feasibility, and that is where the governments can come in. So capital expense, because all these materials, if you're thinking about the solid absorbent, you are purchasing it. So it's a one-time purchase. If it is lasting for 5 years, you are done for 5 years. Who pays for the money? If the government comes and say, well, I will pay 50% of the money that you have, or I'll give you a tax break and all of that, it becomes economics becomes completely different. So this part is something which you need to consider, and then combining everything, an economic analysis is essential, and you must do it by considering the uncertainty, consider different scenarios. So as I said, for any selection, it's very difficult to analyze it without going all the way up to the economics, because there is no clear winner for these technologies. That is why we are developing all technologies. Can you come up with a technology that is very selective, operate at low partial pressure of CO2, but has got very low heat of adsorption? It's a challenge for you, all the researchers in the world. If you can do that, you will be a billionaire. Nobody has the technology. That's where all the challenges are there. Unfortunately, there isn't nothing that we could come up with so far. So that's a challenge for our future researchers. Hope somebody will come up with something in one of those days, okay? So I'm not sure where we are doing at the time. I think maybe at the lunch time, right? Already coming. 12:45. We're supposed to end at 12:30, right? This one, or? Okay, I'm mostly done actually. I just basically wanted to say, take about 5 to 10 minutes. Concluding remarks are that we need considerably high effort all over the world for decarbonization, and CO2 capture is one out of many options. But remember, this is critical for many countries. Many countries, like I know in the United States, one of the big advantages that they had was the availability of the shale gas. So natural gas, because that itself dropped the CO2 emission considerably. And then, of course, they don't have solar like us. Only some states have the solar. So India, for me, it seems like the solar is the great option. But the problem with the solar is massive capital expense there. So that's where the problem that comes there. So if we continue to use coal, then the CO2 capture is one of the critical things that is important there, because we cannot get rid of the carbonaceous fuel such as coal for a while. Adsorption is a very valuable technology from varieties of sources. Another advantage of the adsorption is that you can just almost put them anywhere. Like that's why a lot of these direct air capture technologies people are considering adoption, because you can put it in the middle of the city actually. I do know there was also a project, it's probably Netherlands or Norway actually. They had the projects like installing it on all cars that drive around the city. So had almost like a canisters, it's a solid German. So it just put it in all cars. So as you are driving there, so it captures CO2 from the ambient and also emissions from your car exhaust, right? It captures there, and then at one point you open up the canister and put it at a place which collects everything and dissolve at some other location. So that was a very nice concept that you could do this capture and they do the regeneration at one place, but capture in a distributed manner. So that also can happen. As I said, that you must select it very carefully by considering number of factors. And this was my view. I will say that in my view, economics is the final thing, which gives you everything. If you can say, this will cost me so much of INR, that clicks with everybody. Like if you go to a political person, you go to a social, go to somebody in the community and say, first question come, how much money we need to do this? This is the first question without understanding all the technical aspects here, okay? So questions and any other thoughts anybody has. So first I'll check any questions anybody has, any clarity, any questions for the adoption. Yeah, speak up, don't be afraid. Like we'll be here for next 5 days, speak up and we'll answer questions. Yes.
So one question, sir. So regarding the commercial aspect and how energy intensive it is, as per my understanding, so absorption and deabsorption means when it is releasing the CO2 for utilization, deabsorption would require much more energy than whatever the energy it has been utilized for the means absorption process. So on that basis, sir, one though not related to this one, so as you mentioning that we need to find out the solution, what is the best cost effective way. I'm trying to understand from you, sir, what is the prospect of carbonic anhydrase using those kind of catalyst and so for this direct air capture or from the point source? So I'm just trying to understand from your point of view.
Yeah, this is a different aspect also. Thanks for bringing that angle. There are a lot of actually all the catalyst as well as that could be producing some chemicals. Those could be considered there. So in those cases, you do not need the desorption energy because you are not releasing the CO2 at all. The point here is what you have to keep in mind, that if you can come up with a clever chemical that has that level of market demand and utilization, then yes, of course. So in that case, you adsorb, you do not have to desorb there, and you can save money there from this perspective. Problem is that most of the chemical that people have been thinking about, including also a lot of putting it in the cement and building it and putting it in the building materials and all of those, lot of thoughts are there. But yes, so it is possible, but there is not a single product that has got that much of a demand that can take that much of CO2. But it will be, we need many solutions. That's the thing. So there is a market for lot of options. So there is not a single solution to this problem. So of course, we should explore those utilization approaches that does not require you to dissolve. There is also a lot of discussions in terms of what we call the reactive CO2 capture. We'll not be discussing it here much. The reactive CO2 capture basically means is that you are capturing CO2 from within the source where it is getting produced and producing a value-added chemical right there. So it basically means is that you do not need to capture the CO2 separately, but at the source where it is being produced there. So those thoughts are also there. Okay, other questions, comments, discussions? We are ready for lunch? Okay, anybody online, do you have any questions? I hope we can see the Should I go for stop and see if anybody has anything on chat? Yes. Okay, yeah. Dr. Sridhar already said if you have any question, post it. Yeah, anybody online, please let us know if you have any question. Already? Okay. Thanks, everybody. Yeah. Take it off. Already. Okay. Thank you. Oh, chemistry. Okay.
Good? All good? Okay. Okay. Good afternoon, everyone. So for next 2 hours, we will be kind of like focusing on the fundamentals of adsorption. So this is nothing to do with carbon dioxide in specific, but we actually deal with what is adsorption and what are the fundamentals and what are the things we have to look into the adsorption. So if you have done like BTech in chemical engineering, adsorption chapter, so some of the topics are covered in that one, but just for the sake of clarity, we kind of like also go through some of the fundamentals as well. Okay. So look at this one. This is like in the first 1 hour, we kind of like try to cover what is adsorption, what is the basis, how adsorption happens, what kind of like things we have to consider. And the second one, coming to the adsorbents, what are the existing adsorbents, what are their characteristics, what exactly we wanted as a perfect adsorbent, right? And so there may be so many adsorbents available in the market, but some of them are industrially useful. So why these adsorbents are industrially useful? What are those characteristics? So we will actually go through those parts, and then finally we kind of like talk about adsorption equilibria, like different types of adsorption isotherms. Especially it is nothing to do with the models. That means that we don't talk about Langmuir model or BET model or Friendlich model or whatever. We kind of like talk about what are the characteristics of an isotherm, right? So those things we will talk about here in the first 1 hour. So you all may know that what is adsorption, right? What is adsorption? Right? So adsorption is ability of certain solids to kind of like absorb or to some of the components, one or more components. It's like not just one, it may be more components from a liquid or gas mixture, right? So it's not only for the gases, although here we kind of like specifically talk about gas adsorption. Adsorption can also happen with the liquids. So some of the components can be adsorbed from the liquid solution to the solid. So anything when an adsorbate, here we see here, oh yeah, sick, sorry. So here this is the process adsorption. So the solid we call it as adsorbent. So whenever I say adsorbent, that is solid, and adsorbate is either gas or liquid, most likely gas in this case. Okay. So this process we kind of like most likely use in industry, kind of like removal of moisture. So that means that water vapor, to remove water vapor is kind of like you put a solid, you kind of like try to absorb those water molecules onto the solid surface, and the other gases is like moisture free. So this is because when we have like moisture in the stream, it's like the system is probed to corrosion happens. So that's why we have to remove the water. So the most of the cases that's what they do. But the same process, same process can be used to separate the gases, especially some of the gas mixtures like xylene, methane, ethane, propane, nitrogen, and so on and so forth. Because to separate some of these gases using the existing techniques like distillation or absorption, which is it's kind of like these are energy intensive operations as well as they are actually like very costly. So that's why we kind of like use adsorption in that case. Okay. So let's go to the basic difference. Maybe you kind of like have a thing into your mind. So always remember absorption and adsorption are two different processes. So these two things together, some people call it as sorption. When you say sorption, it can be absorption or adsorption, right? But these two are not same, right? So whenever you talk about absorption, that is like something to do with the bulk, and when you say adsorption, AD, that is something to do with the surface. Okay. So although there are like so many differences which you can go through it, which I will not go through each one by one, but one thing I kind of like want to tell you that whenever we talk about adsorption, note that it's a surface process, right? It's not a bulk process. So like look at this one, this is the only thing I want to tell you. So the one which you see here, this is the one. So this is the adsorbate, right? So whenever adsorption is happening, so the one you can see here, right? So this only, we are only talking about the surface process here. Nothing enters into the bulk of the thing. Whenever you talk about the absorption, it is kind of like a mix. It's a bulk process, right? So although you see here, this is adsorption, this is absorption. Just put it like that. Okay. Right. So this one, when it comes to the adsorption, right? So we kind of like focus on the adsorption. Then we can see that there are two types of adsorptions. One is physical adsorption. So that only deals with the van der Waals interaction. And you say chemical adsorption, which kind of like whenever there involves a van der Waals bond, like sorry, a covalent bond, right? So whenever we talk about chemical adsorption, we are talking about something to do with the bonds. Whenever we talk about the physical adsorption, we talk about the van der Waals interaction. That means that there is only attraction between the surface and the molecules. So that's why they come and adsorb onto the surface, but there is no chemical bond involved in this case. Okay. It's muted. So whenever we talk about physical adsorption, one thing you all remember, this is a reversible process. That means that the adsorbed molecule will kind of like again go back. That process can, then that process is called desorption, so which we most likely don't deal with it. Okay. And whenever we say chemical adsorption, we say it's irreversible process because the bond have formed, so it is not fully irreversible in most of the cases. And heat and all, we will talk about the heats whenever a gas molecule adsorb onto the surface, what kind of heat will be released and how much the heat and what to do with this heat. This all we will deal with the thermodynamics of adsorption, which will come tomorrow. So we only like in this today, like maybe in this lecture and the next lecture, we will only talk about the physical parts of the adsorption. Tomorrow we talk about the thermodynamics of the adsorption. Okay. So when it comes to the adsorption, this is the very important thing. Adsorption, whenever we say adsorption happened, a separation happened, it may be because of the three reasons. So one is the steric interactions. So steric interactions means that you have a solid surface which is adsorbent like this, right? So this is the pore structure which may be available in your adsorbent, something when you look at the nanoscale. right? So whenever you have two gases, so one is a small molecule and one is a very big molecule, something like this. So this force only allows small molecules to go through it. So only this molecule will go through it, and this big molecule will not go through it. Right? So that is called, this process still we call it as adsorption, but it's something to do with the steric thing. Okay. Second one is equilibrium, which most likely we do see. So what happens is that, so whenever you have an adsorbent something like this, you have two molecules, so which both can go through it, but this surface adsorbs this molecule more than this molecule. That means that interaction between the surface versus this molecule is more compared to interaction between surface with this molecule. So then what happens is that whenever this attracts more, so this will go and sit into the pore surface, and this molecule, less molecules will go and sit into the surface. So that is second kind of separation can happen, that's called equilibrium. So third one is called kinetic mechanism. So kinetic mechanism, which we kind of like see, so you have like two molecules. Yeah, this one, they both are same. So this pore structure can accommodate both the molecules. Right. One is this, maybe one is this. So both can enter into the pore surface, but this can diffuse faster and this diffuses slower because of several reasons. One may be the size, two may be the interactions, right? So what I mean to say is that maybe if this molecule is strongly attracted to the surface, this molecule will not diffuse faster because it is strongly attached to the surface, right? So even though the gas molecules have more adsorption capacity, sometimes it may be kind of like in terms of kinetic mechanism, it is not good for it. Okay, so these things we will see maybe sometime tomorrow when we discuss about the diffusion resistances. But the third one is the kinetic mechanism, that is because of the diffusion rate, how fast a molecule can enter into the system. Okay. So as I said, adsorption is a surface phenomena, but why we are talking about entering into the pore structure, right? So do you ever think like that? We are saying that adsorption is a surface phenomena, so that means that it should happen just on the surface, not into the bulk. But why we are talking about all these things in adsorption? Right. So it is still on the surface, but surface of the pore, right? So it will not enter into the bulk core part of the system. So here it will not enter. So it just enters through this one, which is still the surface, and leaves it. Okay. So that is the only thing. Right. And the next one. So we will kind of like go through one by one. So as the situation comes. Go. So like first we will focus on the adsorbents. So that means the solid. So what are the characteristics of the solid we wanted, so that we kind of like adsorption is happens in a way we want it. Okay. So usually how we will use this adsorbents is that we kind of like use this like in the form of small pellets, right, or in terms of beads, or in terms of like granular forms. We kind of like split these solid adsorbents into these forms and put it into a packed bed or anywhere in an adsorption setup, and then we will use it. So usually these are of in the size of 0.1 mm to 12 mm size. So it means that these adsorbent materials is kind of like, you say this is the adsorbent. So this is in the order of 0.1 to like 12 mm size, right? But yeah, that will come. Okay, so these are the things. But when, well, like what size we should use, whether we should use 0.11 size or 12 mm size, it all depends on the system to system. So again, which we will kind of like comes into thermodynamics, how we have to choose these things, right? We need to kind of like make sure these things have been taken care of. If the particle is so big, right? So then what happens is that it will offer a lot of resistance because the gas molecules has to flow through this one, right? If gas molecule, if the adsorbate molecule is so thin, like say if you use 0.1 mm, so then what happens is that it will offer more pressure drop to the gases, and it will not have adequate strength. So we kind of like have to take care of all these things when we design an adsorbent column. So we kind of like have to take care of all these things and then choose the proper adsorbate material. And then second one, once we kind of like take care of all these things, the thing we have to look into is adsorptive ability. That means that this material, solid material, how much it can absorb, right? So which is very important thing. So if you kind of like take care of everything, like okay, so you take care of the size, you take care of the shape, you take care of the bed, but still it does not absorb the gases, so it does not good. So that's why we kind of like, first we kind of like take care of the sizes and all, and then second we will look into the adsorptive ability. So how much it can absorb, okay? So third one is highly porous. We want a porous material. If it is highly porous, it can accommodate more gas molecules into the system. So then the fourth one is large surface area per unit weight. So whenever for a unit weight, if you have large surface area, that means that a lot of molecules can go and sit onto the surface because it's a surface phenomena. Okay. So look into the surface area and then pore size distributions, how it will affect, right? So the first one is the surface area. If you have more surface area, so the dissolution rates are very high, adsorption capacity is very high, and whenever the surface area very high, so it represents surface free energy available. That means that more free energy is available. So then whenever there is a chemisorption, so it is good for chemisorption because the bonds can be easily formed when the surface free energy is very high. Okay. So second one is pore size distribution. So we kind of like have to take care of pore size. So this is the adsorbent size, right? So whatever we say 0.1 mm to 12 mm is the size of the adsorbent, right? Inside this adsorbent, what is the pores? Like how big these pores are? So these pores are very small, like that, or very big, something like this, or like what kind of pores are available? It's maybe straight channel, something like this, or a zigzag channel, something like this, right? So all these things matters. So that's why we also have to look into the pore size distribution, what kind of pores are there, right? So sometimes when we kind of like do the analysis, it says that large pores are available. So whenever you see here, so some pores looks like this, right? So some pores looks like this. So whenever you do the pore size analysis, it says that okay, big pores are available in the system. So that means that it actually sees here. So here you can fit a very big molecule. So it says that okay, when you do the analysis, it says that okay, large pores are available. So this much big molecule can enter into the system. But it is not true. Actually, you can fit one molecule here, but if it travels from this place to this place, it has to go through a limiting pore size, which is here, the smaller one. So it will kind of like obstruct the flow of this molecule from one pore to the another pore. So we kind of like have to check what is the pore size distribution. What is the biggest size of the pore? What is the smallest size of the pore? So we need to cross check everything before selecting these materials. So that's what we kind of like talking about diffusion rates. This molecular sieving properties is like this, which kind of like does not allow. And we also have to look about, always we will look into surface area per unit volume because that's what we wanted. More surface area we wanted for adsorption. Okay. So as per IUPAC classification, pores are divided into three types: the micropores, which is the diameter less than 2 nanometers, that means 20 angstroms. Mesopores, which is between 2 and 50 nanometers, and any pores bigger than 50 nanometers is called macropores, right? Whenever we deal with small gas molecules like CO2, we always deal with microporous material. So because CO2 size is roughly like 4 angstroms, right? So we should kind of like choose which is around like 4 to 10 angstroms. If you choose a bigger one, it makes no sense because it allows everything else. So whenever we kind of like want to capture a CO2 molecule, we kind of like deal with pores which is around 1 nanometer or less than 1 nanometer, okay? And these are the different types of the pores available. So some pores are like smooth, something like this. Oh, sorry. So what you can see here is that some pores are very smooth, and here some pores are like zigzag, and here you see some pores are like having like large pore sizes followed by small ones. So this is called cage type pores, right? It's kind of like a cage. It will allow you to enter into the first one, but it will not allow you to flow through it. So it's kind of like a cage thing, right? So we talk about 3 different types of pores, and in terms of size, we also talk about 3 different pores in terms of surface. So that means this is smooth pores, this is zigzag, and this is cage, okay? Let go. So why do you think it matters, right? You just see one example, right? So what has been done here is that you see the same material, which is silica gel, so that is adsorbent, right? So they kind of like created same with the help of same material, but different pore shapes. Sorry, so different pore diameters. So here they have pore diameters of 2.1 nanometer. Here you have see the pore diameters of 3.3 nanometers. And we will talk about adsorption isotherms later, but just look at this one here. On the x-axis you have pressure, on the y-axis you have the uptake, that means amount adsorbed. You see the amount adsorbed in both the cases are different, depends on the pressure. So what happens is that when the pore sizes are smaller, which is 2.1 nanometers, what you see here, right? So at low pressures, it adsorbs more number of gas molecules compared to this one. But when you see at higher pressures, so the one which is having high diameter or higher bigger pores is adsorbing more. So we will see why this is the case, okay? So why there is a transition at low pressures, why this is performing better, at high pressure why this is performing better. Right. So I will not go through it, it's just for the information. So there are several adsorbent materials are available. So they all are like tested either at the lab scale or at the industry level to kind of like separate the gases or water vapor and so on and so forth. So especially nowadays, most of the people are kind of like working on the molecular sieves, which is like geolites, metal organic frameworks, covalent organic frameworks, which we will go through it. And yeah, so especially if in the industry, mostly they will use kind of like to separate the water vapor from a gas mixture. So they use alumina thing. So this is because that it is very easy to kind of like functionalize the alumina. So when you functionalize alumina, which kind of like adsorb the water molecules, because water is a polar molecule. So alumina is one good choice. The second one is the silica gel. Silica gel itself kind of like can attract the polar molecules, and it has high surface area compared to the alumina. So silica gel is one of the option that is available for especially separating the water from the gases, right? And then third one, which we kind of like fully explored, is activated carbons. So activated carbons will have different structures, depends on the nature of synthesis, how you synthesize the material and so on and so forth. So it will have extremely high surface area, high micropore volume, and it is used to separate the gases, even the bigger gas molecules like xylene and so on and so forth. And nowadays, people are kind of like using geolites. So geolites are kind of like industrially using to kind of like separate the gases and water and separating some pollutants from the water as well. So these geolites are of two types. One is naturally available, one is kind of synthetic geolites. So most likely for the gas separation, we use synthetic geolites of different sizes and shapes, which has been shown here. So the new generation of materials which people kind of like trying to explore, these materials are not industrially kind of like explored. It is still in under academic exploration stage on. So one is the metal organic framework. This is like also like geolites, but thing is that it has a metal node connected by a organic linker. So how many linker molecules we have, how many metal molecules we have, and so on and so forth. It can actually form different structures, as you can see here, right? So different sizes, different shapes, and so on and so forth. And these are actually flexible molecules, unlike geolites. So geolites pore structure is well defined. So most likely it's a kind of like crystal, so the pore sizes are almost same at all the time. But what happens with the metal organic framework is that when the gas molecule enter into the system, this metal organic framework either try to compress or expand depending on the interaction between the gas and the MOF materials. And they are flexible systems such a way that when I say pore structure looks like this, but this is kind of like flexible. That means that this kind of like expand and contract all the time. So it kind of like allows the gas molecules to enter into the system. So then next. So this is kind of like you can see that what happens in gas adsorption in terms of MOFs. We are not talking about adsorption isotherms a lot because we did not discuss what is an isotherm. But as you can see here that this MOF material can adsorb CO2 a lot compared to any other gases. So whenever you put a MOF into a system consisting of different gases like CO2, CON2 and H2, it can kind of like only adsorb CO2 molecules and separate CO2 from all other gases, right? So the next class of materials people now trying to explore is covalent organic frameworks. So it is similar to metal organic frameworks. The covalent organic frameworks will not have any metal. So it is connected by a covalent bond. So all the linker molecules are connected through a covalent bond and forms a well-defined structure. As you can see here, the structures are very well defined, and yeah. So then next class of materials, which is just coming up, maybe a couple of people are explored so far for the gas separation, especially for CO2, is that flexible hydrogen bonded organic frameworks, right? So the difference between these three classes is that so when I say MOF, you have a metal and then it's connected through an organic linker and then another metal. So it's like this, just giving one example, right? So it's a very well defined structure, something like this. Whenever we say covalent organic framework, we will not have any metals here, right? So these linker molecules are connected through, these organic linker molecules are connected through another covalent bond. So that is covalent organic framework. Whenever we say hydrogen bonded this one, so they are not connected by a covalent bond, they are just connected by a hydrogen bond. So physically there is no bond, but only if hydrogen bond exists. So these materials are showing very good performance for the gas separation. You can see even like molecules of similar size, C2H2 and C2H4, right? It is only taking C2H2, it is absorbing C2H2 but not C2H4, although both have similar size, right? So these are the new generation materials that are coming up now, right? So now talk about adsorption equilibria. So what is equilibria? Rate of adsorption is equivalent to rate of desorption, then it reaches an equilibrium. Yeah. So whenever you have a surface, that is, you have an adsorbate material, right? So then it's kind of like allow sufficient time to interact with an adsorbent molecule, right? So then what happens after some time, the rate of adsorption is equivalent to the rate of desorption, and then we kind of like can say that we reached an equilibrium stage, right? So like that at different pressures we try to kind of like understand how much it adsorbed, that come on, yeah. So that we can kind of like call it as an adsorption isotherm. That means that at 100 bar pressure, at 100 mmHg pressure, so how much it adsorbed at 0 degrees. So for example, you see here it's around 60. So at 200 you measure, 300 you measure, 400 you measure, and then you draw all the points on pressure versus amount adsorbed. That's what we call it as adsorption isotherm. So because we are calling it as an isotherm, it is because it is all the measurements are happening at constant temperature. So this adsorption isotherms depends on the temperature. Okay, that's good. What else? Yeah. So coming to the adsorption mechanisms. So whenever we say adsorption happened, it can happen in three ways. So one is monolayer adsorption. That means that whenever we have a surface, the gas molecules will only adsorb on the surface. Okay. So that means only one layer of gas molecules can adsorb on the surface. So that's called, we call it as monolayer adsorption. So whenever we say multi-layer, that means that still there is a surface. So then monolayer adsorption happens. On top of those gas molecules, another gas molecule will come and adsorb. So this is second layer and that is third layer. So this is called multi-layer adsorption. So last one which we kind of like talk about is the capillary condensation. So this happens a kind of like a pore. So for example, you see this is a surface here. So this is a surface here. So here monolayer adsorption happens. On top of which you see here second layer of adsorption happens. So then the pore becomes like a small one. So where the gas molecules condense and forms like a liquid, right? So this is kind of like called capillary condensation. So this is a third type of mechanism that can happen in any adsorption process. Okay. So whenever we kind of like try to see a adsorption isotherm, based on the adsorption isotherm, we can say that what kind of adsorption happens. So that is the thing. Oh yeah. Okay. So that's the thing, we will kind of like go through it. Like, so when monolayer adsorption happens, how the isotherm looks like. When a multi-layer adsorption happens, how an isotherm looks like. When capillary condensation happens, how an isotherm looks like. That's what we kind of like discuss in next few minutes. So this is a simple slide where it actually shows like whenever you have a pore something like this. So this one here you see this is a monolayer adsorption. So here you see it's a multi-layer adsorption, you can clearly see. And then where you see here, so a monolayer adsorption followed by a capillary condensation. Okay. So let's look at the type 1 adsorption isotherm. So there are 6 types of adsorption isotherms, so which we will kind of like look into. So the first one is type 1. What do you observe here? So here, although I did not mention here, the x-axis is the pressure, y-axis is the amount adsorbed. What you do see here? So this is kind of like I have both adsorption isotherm and desorption isotherm. So both looks like that. So that means they follow exactly the same path. So what are the characteristics of type 1? You see that this is a pressure axis, right? And this is amount adsorbed. Even at low pressure, right? So just low pressure, the amount adsorbed increased exponentially, right? So it reaches equilibrium very easily. Look at the characteristics. So one, look at the curve type. It's a concave to pressure axis, which you can see. So this kind of like process happens typically in micropores. That means less than 2 nanometers. So adsorption proceeds at best up to the formation of the monolayer. So it means that it's a monolayer adsorption happens. So that means that when the surface is there, it's only one layer it forms. So this is good for solutes that present in low concentration. Okay. Why? Because only monolayer adsorption happens. That means that amount it can absorb is kind of like limited. So as long as the surface is available, it will adsorb, otherwise it will not adsorb. So in that case, we kind of like, it's good for solutes that present in low concentrations. And what you see here is that relatively high solute loading at low pressure. So at very low pressures, it kind of like absorb a lot of gases. So these are the characteristics of type 1. Let's go to the type 2. So here also, as you see, adsorption and desorption follows the same path. But what you can see here is that a knee kind of structure. So like this with an inflection point somewhere here, right? So that means that this is a characteristics of multi-layer adsorption. So then what happens is that when you kind of like have a, oh my God, always I use. Right, maybe I will write like this. Right, so you have a surface like this. So at low pressure, so the gas molecules will come and sit on the surface, something like this. Okay, so that's where from starting from here, it will go until here. So after this point, then the gas molecules started sitting on this. So that's why as the pressure increases, so the adsorption may happen something like this. So that's why as the pressure increases, the uptake increases. So this is like first layer and then go on. So it is most likely a multi-layer adsorption happens here. And then second thing you see, this whenever you observe something like this, it only because of the physical adsorption. This is because in multi-layer adsorption, in chemisorption, multi-layer will not happen because a bond should form between a gas molecule onto the surface. So it can only form bond here, but not from here. Okay. So whenever there is a multi-layer adsorption, most likely it's a physisorption. So this is type 2. Okay, let's go to type 3. What type 3 says? So again the same one, adsorption and desorption follows the same path. So anyhow the shape, the first one talks about the convex to the pressure axis. This happens when the gas molecules strongly interact with the gas molecules rather than the solid surface. That means that when you have an interaction between gas and gas, and you have interaction between gas and solid, right? So first one here, second one here. So what happens at the low pressure, right? So when you say nothing is here, just solid surface is there. What we are saying is that gas-gas interactions are greater than the gas-solid interactions. So that means that these gas molecules happens when gas-gas interactions are stronger than the gas-solid interactions. So that's why initially it is pretty slow, after that it increases exponentially. Oopsie. Right, coming to the type 4. So here is the first time what we are seeing is that adsorption isotherm is not following the desorption isotherm. So there is a change in between somewhere. So this is kind of like happens whenever there is a capillary condensation. So when a gas molecules, like whenever there is a capillary condensation, what happens is that these gas molecules condense into the liquid. So it requires more energy to convert liquid into the gas. So that's why it does not follow the same path, it follows a different path. Okay. And then second thing what you see is like alternative things. So that means this is monolayer, second layer, third layer, and so on and so forth. So type 5 is exactly same as type 4. That means that adsorption and desorption does not follow the same path. But this happens when gas-gas interactions are stronger than the gas-solid interactions, right? It is exactly like what you can see is that type 4 is actually equivalent to type 2 with capillary condensation, and type 5 is equivalent to type 3 with capillary condensation. Okay? So that's what you see here. So one thing we all have to understand from all these things is that whenever adsorption isotherm and desorption isotherm does not follow the same path, that means that capillary condensation is involved. Okay, that is one thing which. Okay, type 6 is a very good one. It's like a very good student. So what happens is that in type 6 adsorption isotherm, so the gas molecules kind of like follow a same pattern. So this happens when the solid surface is uniform. That means that first the gas molecules will try to fill all the surface pores, that is here. So that means from here to here a monolayer will form, then it starts filling the second layer. So like this. Once the second layer is done, then only third layer. So that's what you can see, first one, second one, third one, and fourth one. I'll just show you one example where we get this one. Oh, hey, look at this one. So this is the adsorption of krypton on graphite surface. Look at this one, how it actually happens. So there is a peak, that means that all the krypton molecules are sitting on the graphite surface. Once the first layer is full, and then like slowly it goes to the second layer and then third layer. Okay. So these are the 6 types of adsorption isotherms which we kind of like talk about. Whenever we see these adsorption isotherms, we can actually come back and say like, okay, what kind of a process or mechanism happening in the adsorption, whether it's a multi-layer adsorption or monolayer adsorption or capillary condensation is involved, or it forms layer by layer. So look at the adsorption isotherm and go back to the mechanism and see how it is happening. Okay. So any questions? So anyone from online? Right. That's good. Oh yeah, sure. Yeah. Metal organic frameworks. Usually, whenever we deal with gas molecules, that it's still at the lab stage only. Whenever we do these things, adsorption and desorption follows the same pattern because most likely capillary condensation may not happen. So, but however, it depends on the system to system. So whenever you kind of like try to separate CO2, methane, and so on and so forth, small gases, water vapor, using metal organic frameworks. So adsorption and desorption follows the same pattern. Yeah, so.
Use molecular sieves for adsorption. It's okay if I say.
Yeah, okay.
Yeah, in our air separation plant, we use molecular sieves for adsorbing CO2. Okay. There we are using nitrogen for the case of desorption.
Desorption?
Yes.
Okay. No.
That way, do we require any other medium for the desorption part of when we deal with metal organic frameworks?
Like I mean to say, when you adsorb it, you are adsorbing CO2, right?
Yeah, from air, whatever CO2 is present in the air, that
Okay,
is
you
being
are-
adsorbed
Okay,
using
and
molecular
then,
sieves.
okay, and then like whatever nitrogen also adsorbed, you try to
No,
dissolve.
no, no. For the case of desorption, we will be sending nitrogen in the opposite direction,
Okay, so that it
which
is.
will remove the trapped carbon dioxide from the molecular sieves. In same way, if we use metal organic frameworks as the adsorbent material, what will be the medium used for desorption purpose?
So during the purging, I guess you are talking.
Yes, yes, sir. Because it is cyclic.
Yeah, we generally use any inert gas. Okay, that should not adsorb in the like either metal organic framework or the zeolite. Okay, by the time it would whatever the adsorbent that is present in the gas phase, that will come out during the purging phase.
Mm-hmm.
Okay, that's how it would be.
So any inert gas like a nitrogen or a
Yes,
will be sufficient with metal organic frameworks
we
also.
use nitrogen.
Yeah.
That is most available.
Yes, yes, sir.
Two gases, it comes with CO2.
Mm-hmm. Okay.
Yeah, okay, purging. Yeah. Adsorption capacity depends. Yes, it depends on layer to layer. Yeah. Right.
But after that, the next layer it comes, it just saturates. Then again it increases, because the interactions are between layers. It is not between the surface and the layer.
Yes, but no. Okay, so what you're talking is here, right?
In this one only, type 6.
Okay. So here what happens? Here the gas molecules are interacting with the surface first.
Yeah.
Right. So then it's like then the second layer starts.
Yeah.
So this is the second layer of adsorption. Okay. So until it kind of like reaches that full second layer adsorption, so it kind of like, you see, this follows a similar trend. I mean to say the adsorption capacity is almost same because it forms on the first layer only.
No, my question was actually with respect to type 6. Can you go to the slide 26?
Oh, it's
type 6. Yeah.
Okay.
So, yeah. So in this case, the first increase from 0 to 1 is because of the interaction between the surface and the gas molecules.
Surface and the gas molecules.
Now
yes.
the first layer is absorbed, which
Yes.
we call it as monolayer.
Yes.
The next layer is going to come up, which is going to get absorbed on the first layer.
First layer of the.
So there the absorption capacity is nearly saturated. It stays around 1. It
no,
stays around 1.
You can see this one, right? See, okay, you are following this one or this
Yeah,
one.
yeah.
You see, here it goes from 0 to 1.
Yeah.
Right. So second one is kind of like say 0.8 or whatever.
This which is staying around 1. This is like on the monolayer. The adsorbates which are going to get absorbed on the first layer.
First layer, right?
Now this first layer is done.
Okay.
And this second layer is also done, which is around 1. Now the third layer is going to come up, wherein we are seeing a high uptake between 1 and 2. So why this jump between the layers?
No, wait. See, let me tell you. So this is the first one you understand, right? This is between the gas and the solid.
Yeah.
You just look at this one.
Yes.
So from here
is the gas to gas.
Like here is like gas to gas.
Okay.
Right?
Okay.
And this is gas to gas. Here there is no adsorption. You see this, like as the pressure increases, there is no adsorption happening here.
Okay.
Right?
Okay, there is no adsorption.
No adsorption. Right. So you kind of like have to increase the pressure so that the gas adsorption starts happening.
Yeah.
So then after this second layer, this is third layer.
So this is limited by the partial pressure also, because you have to operate around 0.4.
Obviously, yes. So okay, you are talking about this is gas alone.
Yeah,
That is not the one.
Can you go to slide 23?
Slide 23, yeah.
So what about heat of adsorption in this particular case?
No, we'll talk about heat of adsorption when it goes to the thermodynamics. We'll go and discuss each case.
And in type 2, you mentioned about non-porous powders. That type 2 is preferred in non-porous powders.
Type 2?
One of your points say that.
Yeah.
The second one, the most frequently found when adsorption occurs in non-porous powders.
Non-porous powders.
What do you mean by that?
So what happens here in type 2? So here, like you see here at low pressures, so the gas try to adsorb here, right?
Yes,
that means
yes,
that
sir.
solid gas interactions are very high.
Yes,
So it's like peak is there, right?
Yes, sir.
So whenever you have like a non-porous powder, so that means that adsorption only happens on the surface.
Okay.
right? It's not like porous, unlike. So it only happens on the surface, somewhere here. So it adsorbs initially here, and then slowly it goes. So this is kind of like multi-layer. Microporous, sometimes it can, yes, but you mean to say this much? No, when it's a microporous, right? In between micro and meso. Oh, why do you think so?
No, because like there are two patterns that are being reflected here, like type 2 spot, type 1 spot, and as well as actually type 3 spot. Because like in the higher pressure conditions, we are actually having an inflection. That's happening. The same thing actually in type 1 spot, actually we are actually having a micro at low partial pressures. You are actually
absorbing more.
Won't that be a combination of intermixing of both microporous and mesoporous combination?
Okay, so so most likely this happens in non-porous powders. Like why we are saying is that, like what you say is that a sharp uptake is there, so that's why it can be microporous, which we are referring to. So when you say it's a microporous, right? So that means that some pores are available inside. So it's try to fill everything here, right? Right. So say for example it's a microporous now, and the second one is that after this point, now all the pores are filled. So still the gas adsorption is there. So where it is coming from?
So that should be actually between gas-gas interactions, right?
Right. So that means that you mean to say it's kind of like coming in somewhere in between.
Yes.
So whenever there is kind of like somewhere in between these gas molecules are adsorbing, then the condensation do happen. So then this does not follow the same path. Okay. So because that hysteresis is not there, which we kind of like talk later. So now we can say that, okay, so these gas molecules are not kind of like coming in between. So there is no condensation happens.
So, but it will also depend upon the pore size distribution parts also.
Right. So it also depends on the, like, if you have a bigger pore, something like this, right? Yeah. Oh. Right. So maybe one layer, one layer, one layer, one layer. Even after some time, okay. So the condensation should happens. Okay. So it is not happening at least until we reach the saturation. Okay. So that's why we kind of like, but still it can happen. Like if it is like, it's a huge thing, like say in between 2 to 50 nanometers. So if we kind of like don't go into the condensation region, yeah, it can happen. But it most likely happens. That's like most frequently found. It's not that always found.
MOFs usually have similar patterns like this.
Yes, it's do, right. Yeah. I agree. So especially in MOFs, whenever you see these things, you also like experimentally also you see the condensation also. Like condensation do happens. Like I mean to say, you see the hysteresis loop in MOFs. Yeah, the too narrow, right. Yeah, because we are not going to that far. Like in MOFs, usually the pores are of 2, like I don't know, even 2 nanometers is big. 1 nanometer only we have, but yeah, that's true.
So there is one question from online participants. It is just now, I think Professor Ravi answered. It is regarding in MOFs and CAFs, which type of adsorption happens, and what about amine functionalized MOFs?
Okay. So this functionalization and all we will come back, like we will do it. We have like a class tomorrow which we kind of like discuss about the diffusion and then the effect of functionalization. That time we kind of like, yeah, try to discuss thoroughly about the functionalization. And yeah, so anyhow, I think we kind of like have discussed what kind of adsorption happens in MOFs is that usually we observe type 2 in MOFs as well because it's kind of like monolayer adsorption do happen on MOFs.
So, and also it is better we classify these isotherms based on the pore size, like as Professor Ravi was telling, microporous, mesoporous and macroporous, because MOFs, there are MOFs and CAFs which may belong to either mesoporous and microporous also. So it is always concentrating on the pore size. Based on pore size, you can classify them. Okay.
rather than the type of material.
Yeah, that is better. Please continue.
Okay. So any other questions? That's good. Okay. So in the second part, what we kind of like go through is we kind of like, talk about the models. So first we talk about the performance matrix, like what are the performance matrix for the adsorbent materials, and why pure gases we needed, because usually in industrial scale we never see pure gases. Why we need pure gas adsorption isotherms? But here why we kind of like trying to explore the pure gas adsorption isotherms, and then this is the models, pure gas adsorption isotherm models, and how to actually measure it. One way is applying the experimental techniques, one way is through simulations. How can we measure the pure gas adsorption isotherms or mixed gas adsorption isotherms? So these are the things which we will be covering in the second part. Okay. So these are the two things which we always look for. So one is the equilibrium adsorption capacity, one is the separation coefficient, right? Whenever we look for a material, we kind of like look into the two performance metrics. One is the what is the equilibrium adsorption capacity, that means that how much it can hold for, right? How much it can uptake. And second one is what is the separation coefficient, right? That means that with respect to the other gases, so how much it can absorb. So that means that like when you say the first one, you can say it absorbs 100 kilograms. So that is a very high number, but it also absorbs 100 kilograms of other gas, you will not get any separation factor, right? So these are the two things which we always look for. So one is the adsorption capacity, one is the separation factor. Okay. So before exploring this one, we kind of like just go through the same process. Again, everything is same. Okay. How these adsorption isotherms are affected, right? So one thing why we kind of like try to explore the pure gas adsorption isotherms, right? Why we need pure gas adsorption isotherms? Because anyhow we are separating two or more gases. So why we kind of like try to explore pure gas adsorption isotherms all the time? First thing, we kind of like try to get the information about the porosity, pores, and when there is only one gas, how it is behaving, right? So we kind of like try to get the ideal information. Okay, in ideal case, what is happening? How much it can absorb, right? First thing. Second thing is that once we know the pure gas adsorption isotherms, we can always predict the multi-gas adsorption isotherms based on the pure gas things with some assumptions, obviously, right? So this is the reason why we kind of like try to see what is the pure gas adsorption isotherms all the time, and once it is done, we kind of like go for the multi-gas. Second thing is that multi-gas absorption is always difficult to conduct. Experimentally, it is always difficult to kind of like get the multi-gas adsorption isotherms. So it is super expensive. So therefore, what we can do is like one of the cheapest way is like try to explore the pure gas adsorption isotherms and use it to predict the multi-gas adsorption isotherms. Okay. So how temperature affects the adsorption? So we will not get into the why adsorption is exothermic process, which we will see tomorrow. Whenever we say heats are involved, temperature is involved, we will deal with tomorrow. But for the sake of discussion, we start with, because adsorption is an exothermic process. That means that whenever adsorption happens, heat releases, right? So temperature significantly play a role in adsorption. So temperature will not play a role in absorption, AB. It will play only in adsorption. So what Le-Chatelier principle says? So whenever you deal with an exothermic process, right? So at higher temperature favors a condition that evolves less heat. When adsorption happens, heat evolves. Le-Chatelier principle says for an exothermic process, high temperature favors evolve of less heat. If you have to evolve the less heat, it has to absorb the less amount. So that's why as the temperature increases, adsorption isotherms, you see the adsorption capacity decreases. So usually that's why adsorption usually happens at room temperature, not at higher temperature. Okay. So that's what you can see. As the temperature increases at the same pressure, the adsorption capacity decreases. Okay. So yeah, so this hysteresis I think we kind of like discussed. So whenever, always remember the point that whenever there is a capillary condensation, there exists a loop. So that is because of the capillary condensation. That's only one thing you have to remember. But yeah, we go for Langmuir adsorption. So we try to see when we kind of like discuss the isotherms, types of different isotherms, right? We try to understand what kind of mechanisms may happen based on the curve type. But we now kind of like try to build a theory what is exactly happening on an isotherm. Okay, so these are like theories. So when I say Langmuir adsorption isotherm, it's a theory. It has several assumptions, and based on the assumptions, they built a theory, right? So this Langmuir adsorption theory is based on the kinetic point of view. You all know kinetic theory of gases, right? So based on the kinetic theory of gases, they kind of like build this theory. So what are the assumptions, right? So they assume that in Langmuir theory, the surface is flat, right? So maybe it's inside pore or maybe exactly on the surface. The surface is always flat, something like this. And on the surface you have sides which can accommodate the gas molecules. They can accommodate only one gas molecule at a time. It cannot absorb more than one gas molecule. So it actually is, because we say all the sides, this is all sides which can actually accommodate the gas molecules, they are energetically same. So that means that when a gas molecule comes from the gas phase, it may go to the any site with equal probability. Okay. So now you have a surface something like this. So a gas molecule is coming from the gas phase and trying to adsorb on one of the side here, right? So what is the rate of striking a gas molecule when it comes from a gas phase and striking a surface? What is the rate of striking based on the kinetic theory of gases? Remember? So that's anyhow, that will come back. So it actually go with something like this. So it depends on the mass of the molecule, temperature, on the pressure. So this is the rate of striking. That means that the gas molecule which comes here, it may adsorb or it may go back. So it's nothing to do with adsorption. It's like kinetic theory of gases. It does not talk about actual adsorption. It only says, okay, so when a gas molecule is kind of like flowing, it kind of like on a flat surface. So the rate of striking is given by this one, right? That's the pressure 2m kBT. So this is kind of like collision theory, which we kind of like call. It collides and goes. So that is the rate of striking, all right? It depends on all these parameters, temperature, mass, and so on. Say for example, a gas molecule comes here and strikes and goes back, comes here, strikes and goes back, comes here, strikes and goes back. And some molecule may comes here, hit at this site and adsorbs. And it kind of like sticks to the surface. Okay, so this rate of adsorption, which we kind of like write RA, so this is rate of striking. That means it's directly coming from kinetic theory of gases. So then rate of adsorption, maybe we kind of like put another column called alpha. this alpha actually talks about if this molecule is striking the surface 10 times, maybe out of 10 times, 2 times it may adsorb on the surface. It talks about fractional number of molecules that adsorb onto the surface after each strike, right? So this alpha talks about the fractional. So that's why Rs is replaced by Ra. This is called rate of adsorption. That means that like 10 molecules are colliding with the surface. Out of 10, only 20% is adsorbing. That alpha is 0.2. So this becomes rate of adsorption. So this may be true for the first molecule. So the first molecule comes and sits here. But what about the second molecule? Because it's already filled, the second molecule cannot come and sit here. So it will only can sit in the other places. So the second one, the rate of adsorption is P alpha square root of 2 mass times kBT. Kb is Boltzmann constant and T is temperature times 1 minus theta. So theta is fractionally occupied. This is the total, this theta, which we kind of like call something like this. So this is the total number of sites, and this is occupied sites. So this is the remaining. So this is the fractional occupied sites. So 1 minus theta is the available sites, right? So this is, you kind of call it as now, like although I said in terms of volume, but you can call it in terms of sites also. So for example, you have 100 sites, out of which 20 is already full. So alpha becomes 20 by 100. So 1 minus alpha is the available sites. Sorry, 1 minus theta, sorry. So that's where, so that is the rate of adsorption. I am just writing that one. Rate of adsorption is equivalent to P is pressure, alpha, which is number of successful strikes, and then this one. So what about rate of desorption? So to desorb a molecule, it requires some energy, right? Because whenever a molecule come and adsorb, we said that it's an exothermic process, it releases some heat. To send this one back, we again have to supply some energy. So it's we need some energy. So maybe that's an activated process that we can kind of like deal with Kd, which is an equilibrium constant, times, we write it as theta because only theta number of sites are full. So any molecule can go back. So this is the rate of adsorption and this is rate of desorption. At equilibrium, rate of adsorption is equivalent to rate of desorption. You kind of like equate these two things. Right. So this is rate of adsorption. KBT, oh pi is missing all the time, shit, okay. KD theta. Because this is an activated process, you can kind of like write. Something like that. Because this is rate constant. It's an activated process. So this is whenever you write, right, anything you can write, like for example diffusivity also you can write for all activated process. something like this. On the similar lines, Kd you can write, this is the rate of desorption that corresponds to the infinite temperature, exponential of minus Ed. So this is activation energy for the desorption, that is equivalent to the heat of desorption, RT times theta. So you just kind of like rearrange this one, what you get is something like this. Theta is equivalent to Kp over 1 plus Kp, where K is a constant which will take care of all the terms available here. Either you say this one, and yeah, this one, everything will go into the K. So I don't know whether I have this one. Yeah. So this is the fundamental basis for Langmuir adsorption isotherm. Any questions here? What you just have to do is like, you know, this is equivalent to this. You just arrange everything into this form. Theta, you have thetas here, and you have pressure here, and everything else is constant, which is K. That's it. You'll get a form something like this. Right, so this K depends on the temperature. So at different temperatures you will get different Ks. All good? So this is the basis for Langmuir adsorption isotherm. So as we see, this all depends on the basis of assumptions which we make here. The assumption is that the surface is flat. The second one is that all adsorption sites have equal energy, and only one molecule can adsorb at one site. So that's why this only applicable to monolayer adsorption. We never talk about multi-layer adsorption. Okay. So therefore, whenever you try to fit a adsorption isotherm.
So there is one question from online participant. Does this mean the lighter molecule will always adsorb faster or more? Rate of adsorption is inversely proportional to mass.
Rate of adsorption is inversely proportional to the mass, right? Lighter molecule?
Yes, the question is, does this mean the lighter molecule will always adsorb faster and more? Faster
More we
or
cannot
more?
say, faster we can say, right? So more or not depends on adsorption and desorption, both the things together. Faster, yes, because it actually, like lighter molecule diffuses faster. That means that it can make more number of collisions with the surface. So it's like more chance that it will try to hit the activate sites and sit. That is yes, but the second one is not correct. So that depends on several characteristics, right? So it's only rate of adsorption. It's nothing to do with the equilibrium adsorption.
Okay, fine.
Yeah, that's it. Yeah. Yeah. So as I said, this is only applicable to monolayer adsorption when the surface is flat, and it has, like, you will never find like a surface which is really flat, and so that's why it has like so many limitations. But we will kind of like come up with other models. But before going to that, whenever we try to fit a isotherm with Langmuir adsorption isotherm, what we do is we kind of like try to readjust things, right? Like what we do, theta is V over Vm. Vm is the total monolayer volume, and V is the actual volume. So we kind of like try to rearrange in such a way that 1 over V is equivalent to 1 over Bp Vm over plus 1 plus Vm. And we try to plot 1 over V versus 1 over P, like Y is equivalent to MXC form. So this is Y here, and 1 over P is X. So that's what you see, 1 over P versus 1 over V. So where the intercept is 1 over Vm, and the slope of the line is 1 over B. So whenever you get the adsorption isotherm data, you try to plot 1 over P versus 1 over V and see if it is a straight line or not. If it is a straight line, it follows Langmuir adsorption isotherm. If it is not, it does not follow. So therefore, because Langmuir adsorption isotherm is so ideal, it only talks about monolayer adsorption and then flat surface. They come up with Freundlich adsorption isotherm. Initially when it started, it has no fundamental basis, right? So unlike Langmuir adsorption isotherm, it does not have any fundamental basis. It kind of like try to fit with a polynomial equation. Whenever you get an adsorption isotherm, you try to fit within a polynomial equation. So the polynomial factor will change. So it will have something like that. Q is the adsorption capacity, K is a constant, P is the pressure, and M is a constant. So here we have two constants, K and M. Both are depends on the temperature only and changes with the system to system. Okay. So, although I don't have something here, but I can tell you one small thing. Right. So whenever you kind of like try to plot the Freundlich adsorption isotherm, right? So what you have on the x-axis is the pressure, what you have on the y-axis is the Q, right? So because we said that M and K are constants, now you just play around with M. Let's go with M is equivalent to 1, so then it's a straight linear equation. Something like this. Q is equivalent to Kp. So the slope is K. Right? So as the M value increases, the non-linearity goes. So like say for example M is equivalent to 2, it goes something like this. Right? So like that if you try to do at home, when M is equivalent to 10, right? It goes like a rectangle. So this value increases suddenly and then goes like this. This may be corresponding to M is equivalent to 10. Say M is equivalent to 3, something like that. So usually whenever we try to fit with Freundlich adsorption isotherm, M is between 1 and 5. If it is higher than 5 or bigger than like larger than 5, so there is something wrong we have to see. What we say is that when M is equivalent to 10, this adsorption isotherm is kind of like called irreversible adsorption isotherm. This only happens when the process is irreversible. It follows a rectangular kind of curve. That's what we see. Okay. I think we are running late. Okay, so the next one is the BET adsorption isotherm. So here we have like 3 others. So this BET adsorption isotherm is actually started by Professor Brunner. So one you see on the one. So Professor Brunner kind of like started building BET adsorption isotherm on the basis of Langmuir adsorption isotherm. It actually follows all the assumptions of Langmuir adsorption isotherm, but it actually includes the fact that it also allows multi-layer adsorption. Okay. So what he said is that in his assumptions, everything else is same. Whatever we did for the Langmuir adsorption isotherm, similar derivation we have to do for BET. But the only difference here is that on the first layer, gas molecules will adsorb on the surface. On the second layer, the gas molecules will adsorb on the gas molecules. So here you will see the rate of condensation. So that means that gas molecules will come and sit another gas molecules that forms like a liquid-like structure. So and then on the top layer of the gas molecules are interacting with the gas phase. So these are the 3 things which he kind of like incorporated into the system and come up with the BET adsorption isotherm, which we will not go into everything. Yeah, it kind of like has a structure like something like this. Theta, which is V over Vm, that is whenever you see theta, that we call it as fractional coverage, and C is a constant, and zeta here is P over P naught. P is the pressure and P naught is the saturation pressure. So there are only two constants, which is C, like there is only one constant actually, C, and then another one comes here, P naught for a given system, right? So this BET adsorption isotherm typically used to compute the surface area. So because it kind of like deals with the multi-layer as well, so it is useful to compute the surface areas. So if you just rearrange this one, what you see usually is that what you just need to do is that in place of each zeta, you just substitute P over P naught and then just rearrange that equation. You will get something like this. So what you have is the pressure here. This is the total volume. It's P naught minus P. This is the saturation pressure. This is the actual pressure. And V over Vm, which is monolayer volume. C is the, like, whatever you say, Q, or C, the concentration, and everything else. Oops, sorry. I think that's C. Got a lot of confusion, but okay, leave it. That's not. So we talk about several isotherms, but okay. Okay. So we talk about different adsorption isotherms, right? So and then different models, but actually experimentally how we measure it, right? What is the procedure to calculate the adsorption isotherms, right? How we will actually measure it. So there are several methods available, but most likely we follow these two methods. One is the volumetric method, one is the gravimetric method. So we will actually go through each method and see how each method works, right? So let's start with volumetric method. Right. So this is the simple thing, but we kind of like see how we do it in reality, right? What we will do it, the principle here is that we measure the volume of the gas adsorbed by a solid adsorbent, right? That is the principle overall. How we do it, we'll do, but this is the procedure. What we have to do, we need to place the adsorbent material in a chamber and introduce the gas and measure the pressure changes. After equilibrium is reached, record the final pressure, and yeah. So this method is suitable for the gases. That means that we cannot use it for the liquids. I will tell you why. And second thing is that this method is very quick than gravimetric method. Gravimetric method usually takes a lot of time to predict the gas adsorption. Okay. Let me see what I have. Okay, so this is a flow diagram, right? What you can see here, right? So although it's shown for the example of hydrogen, but it can be any gas. So the gas enters from here. You have a wall, and then you have a manometer which measures the pressure. So then, yeah. So here we have two chambers. So this is chamber 1 and this is chamber 2. So we know the volumes of both these two chambers. We know V1, we know V2. So how we start is that whenever we try to calculate the gas adsorption, we try to close valve A, right? So initially we close the valve A, so that means that no gas is coming up, and then try to evacuate everything which is there in V1 and V2, right? So we open valve C and discharge everything through B, okay? So then this V1 and V2 is empty, only solid material is there, okay? So now you close C and B, that means you close this valve C and then also valve B. So that means that here you just remove the connection, this closed, and open valve A. So then what happens, the gas that enters goes into the chamber V1, right? That's perfect. So because this is a gas, ideal gas law is applicable, which is PV is equivalent to nRT. So the number of moles of gas which is in the chamber 1 is equivalent to P, is the known pressure, V1 which is the volume here, right, capital V, RT which is, R is gas constant, T is anyhow the temperature which we are maintaining. Okay. So this is the initial number of moles, right? So then what we do, now we also close valve A. Once it fills all V1, we filled everything, then we will close valve A, right? And then only open valve C. So that means whatever gas is there here in this region can flow to this region, okay? So this gas now is expected to right. So from here we can change in number of moles. Sorry, yes, pressure also changes. It's all at the same temperature. So you got it? So what happens? Initially we kind of like fill the V1 chamber with the gas. So that means we know how many number of moles of gas is there, right? So then we open the valve C by closing valve A. So valve A is closed, valve B is closed, right? So this is also a valve. You just like, it seems like this is a valve, right? It's like comes in this way. Okay. So we closed valve A and valve B so that the gas can go from valve 1 to, so like region 1 to region 2. And then we measure the pressure again, right? So that is the second pressure, P2. And it occupies two volumes, V1 plus V2, right? So then you try to find out the difference between NF minus NI. If it does not absorb anything in the solid system, these two should be same. If it absorbs, the difference will come here, which is NF minus NI. So that means this minus this, okay? So that's why we call it as a volumetric method, which we kind of like try to measure the changes in the pressure, right? You got it or no? What we do first? We try to close valve A and C, or like that doesn't matter. Even like you start with, we close valve A, valve B and C is open, and we try to evacuate everything from here. So that means that these two chambers are initially empty. Then we close valve B and valve C and open valve A. Whatever gas enters will go into chamber V1, which we know the volume. So that is the initial number of moles. N1 is equivalent to P1 V1 over RT. How you will know the P1? You close valve B, you close valve C. So here you have manometer, it can measure what is the pressure inside the system. Okay, fine. Once that is done, now you also close valve A and open valve C. So the gas can flow between these two regions. And finally you measure the final pressure, and the volume is V1 plus V2. So which is V1 plus V2 RT, right? If gas molecule does not absorb into the solid, these two are same because the same gas is there. If it absorbs, you will see a difference here. So this is the amount absorbed, right? That is how to do for each pressure. You start with initial pressure and then you have to do it. So this is volumetric method. Yes. Okay.
Basically, assumes that the temperature of V1 and V2 is same,
Yes,
which may
that's
not
why
be the case all the time.
Yes,
Because
that's why
your
we have
V1
thermostat.
is not immersed in the bath.
No, we have a thermostat or bath here, which kind of like always maintains the temperature.
That maintains the temperature of V2 only, not
No, it
V1.
maintains the temperature of the whole system.
Both system?
Means V1 plus V2.
Okay.
Yeah, we always maintain at the same temperature. Yeah. Because gas is allowed to move from one region to another region, obviously it will come into equilibrium. So, right? Dead volume, we kind of like try to fix it in the first stage when we do the initial thing, and then that we will use it for all the cases. Right? So this method is simple, straightforward, but as I said, we assume that the gas follows the ideal gas law. We may not directly apply everything to the liquids. Right? That's why when we kind of like discuss this one here, we said like it's suitable for the gases. Otherwise, we have to, still we can apply, but we have to apply the corrections and everything. So people do it, but it's mostly suitable for the gases. Yeah. Okay. So the next one is gravimetric method, which is simple. Here we no need to do anything. So the system will do everything for us. So it's a very sophisticated system. It actually involves the measurement of the change in the mass, right? You first initially you have the solid material, so you measure it, do the gas adsorption, again measure the weight. The difference in weight is equivalent to this one. But how we measure is the thing. Oh yeah, I think, oh shit, some equation got missed, but it's fine. So, yeah. So here what we should see is that the amount adsorbed is equivalent to, yeah, M2 minus M1. So M1 is the initial mass of the solid. M2 is the after adsorption happens, mass plus gas. So the difference is equivalent to amount adsorbed. So that is a straightforward. Right? How we do it? Let's see, this is the system. We have a gravimetric method, something like this. So like leave all these things. We are only interested in this one. Here what we have is a microbalance, is just like, so here we have a microbalance which is outside the system. It is not inside the system. You see, how this microbalance works is that with the magnetic effect. So magnetic levitation effect will kind of like takes care. So what we have is a gas inlet coming from here, and then we have like two holders. One is one here, one here. Two holders means nothing. We can actually use two samples to do it at one time. So it's like, it's nothing to do with anything. It's kind of like you can have two samples, same sample or different sample, it doesn't matter. So what we do is like, before entering the gas, we try to measure the weight of the solid, and then we kind of like allow the gas at a given pressure and temperature, and then try to see the change in weights in the microbalance. So this is a very sophisticated system, but it will take huge amount of time to get the equilibrium. But the adsorption isotherms that we get from this system is more accurate than volumetric method, because as you see, volumetric method involves some assumptions, right? So these are the two ways we kind of get the adsorption isotherms using experiments. So the third one is grand canonical Monte Carlo simulations, right? So these are the experimental techniques. So far we discussed a couple of them. The last one we kind of like talk about is the simulation technique. So what we have to do here is that we try to kind of like build a system. So that means that when you say MOF or geolite, so we build the structure of the MOF or structure of the geolite and perform grand canonical Monte Carlo simulations. That means that what we assume here is that once the equilibrium is reached, the condition for equilibrium is, what is the condition for chemical equilibrium? Temperature should be same, pressure should be same, chemical potential is equivalent to the same. So what we do here is that we say here we have solid and here we have gas. These are the two phases and these two are in equilibrium. So then the chemical potential of gas in these two phases are equal. So the chemical potential in the gas phase is equivalent to chemical potential of component I in the solid. So that's I in this. So we apply this principle to get it. Right? How we do it? Let's see this one here. So these are the three parts. The first one is that we have to build the structure. So that's like you see a structure of a geolite, MOF or anything, right? And then we perform different moves. Like what move we do? We kind of like assume a fictitious reservoir. That means that reservoir is not there, but we assume that there is something. And then we try to kind of like pick the molecules from there, right? And then try to take a molecule like this and try to insert into the system, right? And then calculate the chemical potential of the molecules. And then compare with the chemical potential of this one, the fictitious reservoir, whatever, like we kind of like try to say, okay, our chemical potential is -5. Okay, so then we start with that and then see how many molecules can enter into the system. And then -4 and then check how many gas molecules into the system. And again this chemical potential can be related to the pressure or fugacity. So that's why we kind of like try to see. In addition to the insertion, we also do the deletion. Like it's not that we always try to insert the molecule, sometimes we delete randomly some molecules and try to compare the chemical potential of the system with the and two other things what we also do is the translation. Translation is nothing but whenever a gas molecule is here, we not only kind of like insert and delete, we also try to move it, translate it and see, because whenever we kind of like do the translation moves, the energy changes and therefore the chemical potential. So we will try to see how it affects. Other one is rotation. What we do, we take a center of mass and rotate the molecule. So why this rotation is important is that, again, as I said, whenever we have a pore something like this, right? So you have CO2 molecule like, so you rotate it, maybe the oxygen will come here. When the rotation happens, again the energy changes. And again we kind of like try to calculate the energy and relate it to the chemical potential and try to again compare with the reference chemical potential. So this how, like these are the 4 different moves which we do in grand canonical Monte Carlo. One is insertion, second is deletion, third is translation, fourth is the rotation, right? So we kind of like do all these 4 mostly in grand canonical Monte Carlo simulations and get the adsorption isotherms. There is one more. This is especially we do it for MOFs or materials which are flexible. That means that when the gas molecules enters into the system not only size, shape can also change, right? It's not just the size but also the shape. So we will kind of like take care of the system deformation using osmotic ensemble, but yeah, that depends on system to system. Usually whenever we perform grand canonical Monte Carlo, we only do this 4 moves. If required, we also have to take care of the cell deformation. Okay, this is actually very important when we deal with the bigger molecules, right? Something like this. So what happens is that when these molecules enters into the system, they try to kind of like either expand or contract. So that times we have to take care of that one. Yeah. So these are the few examples how we kind of like get the adsorption isotherms using grand canonical Monte Carlo. So it's kind of like at different pressures or like in say fugacities. We try to calculate the loading and then this. So what you can see here is that the black ones, the black squares and then triangles which are in the black at 600 Kelvin and 700 Kelvin using experiments, and then the colorful ones here are from the simulations. You can see that even using simulations you are able to predict the adsorption isotherms very well, right? But still you see here and there some differences, but they are not major. You are able to predict both qualitatively and quantitatively very well. Okay, I think with this we can stop. Okay, so with this we can stop, especially we kind of like see whenever we kind of like use gravimetric method or volumetric method, both are good. Gravimetric method is more accurate, like that's why you see precision is very high, and it kind of like depends on the time and then complexity, you need to choose the method you wanted. Okay, so with that we will stop for today here, and then I am happy to take any questions you may have. Yeah. Or I have anything? No, that's.
So any questions from the participants? So any questions from online participants, you can post it on the chat box. Yes, YouTube chat box.
More. Yes, sir. Yeah, just this is regarding the which method you have to select, whether the gravimetric method or a volumetric method. It mainly depends upon the solid and the gaseous particle only. Suppose, no, my question I have not answered. Suppose any fluid gas which comes out from the boiler sections, so it's gas, that gas contains more dust particles, and again gas also there. If anyone wanted to measure the CO2 content of that fluid gas, without knowing the concentrations or solid or gas content, which method he has to select, whether gravimetric method or volumetric method, when he is not knowing the percentage of dust content or solid content.
Okay, so it's it's nothing to do with the composition, right? Whether you use gravimetric method or volumetric method, it actually depends on the accuracy, right? So both methods will give you the adsorption isotherms, right? But gravimetric method, when we kind of like try to extract the adsorption isotherms, they are more accurate because we kind of like directly calculate the mass, change in mass. But here what we are doing is we are trying to calculate the change in pressure and relate it to the mass. So in that sense, this is like more direct, that is little indirect. So gravimetric is more accurate in general, yeah. So yeah, without knowing the composition and so on, I don't know like how we can select. Maybe Sridhar, you have.
So these gravimetric and volumetric methods we use for testing the adsorbent. For example, I have a CO2 gas that is a pure component gas, and I would like to find what is the capacity of specific adsorbent to adsorb how much amount of the CO2. Okay, at a laboratory scale, we have this classification of gravimetric and volumetric. If we would like to see how the multi-component, the flue gas which you are talking about, we can build customized setup, and we need an analyzer that should detect the gases that are coming from the flue gas. So we can make it something like customizable. Yes, some GC will do that job.
Yeah.
Again, we need to calibrate according to the flue gas composition.
What is the people are using the power purpose? Since very old.
Yeah, that is like chemically doing, or else we have analyzers, and it just keep the
Analyzer and
we will be getting all the concentrations.
Yeah, the analyzer should detect what are the gases that are present in the fluids. So there is one question from online participant. Does grand canonical Monte Carlo simulations take in consideration for porosity or cavity of a material?
Porosity or?
Cavity of material.
Okay, so cavity is a different story. Like this is anyhow a challenge with the grand canonical Monte Carlo simulations. See, the problem with simulation is that, see, what we are saying is that we kind of like so we have a material something like this, right? So I'm just will draw something like, so this is a pore structure, right? And what we call cavity is that maybe you have a cavity here. That means that you have a open pore here. But in experimental situation, so there is no possibility of a gas molecule will go and sit here, right? Because there is no path. It actually has to go through this or go through this. But it cannot go and sit here because there is no way. It is like somewhere in between, right? So there is no way a gas molecule can go and sit in the cavity. That is the reality, like in experimental situation. But what we are doing in simulation is that we kind of like assume a fictitious reservoir. That means like all gas molecules will sit here. We randomly take one gas molecule and randomly place anywhere in the system. So sometimes we place it here, sometimes we place it here, sometimes we place it here, sometimes we can place it here as well, right? When we place it here, because solid molecule is already there, it will kind of like reject it, saying like, no, you cannot place a gas molecule here because a solid molecule is already here, there is no space at all. That comes from the GCMC based on the energy calculations. But that will not come for the cavity, because whenever they see a cavity, it says like, okay, you can fit a gas molecule here. Yes, it is possible. That is one challenge with the grand canonical Monte Carlo simulation. That's why what people do is that when they kind of like try to visualize the system and try to find out the cavities like this, where there is no open access, and they try to block with some fictitious molecule. They try to place one molecule which does not interact with any other molecule, but still it kind of like occupies this place. So yeah, these are the some challenge, like that means like when you try to start working on those things, you'll come across these issues and try to fix it. So there are like methods that kind of like fix it. We're just talking about the method, but yes. So cavity is a different story. Pores, yes, it will take care. Cavity, we have to take care. It cannot take care as by itself. Yeah. Anything else?
Yeah.
Can you also tell us what are the inputs required for GCMC solution and what are the key assumptions in this model?
Okay. So what are the inputs required is that the first one, we need to know the crystal structure, right? So yeah, CIFR. The second one we wanted, and especially the basic assumption, is that the interaction parameters. How we know that these gas molecules go and interact with the molecules on the surface. So that is the primary assumption, that whatever we kind of like use Lennard-Jones, typically people use Lennard-Jones 12-6 potential, which requires sigma and epsilon. So this is interaction parameter, this is size parameter. So these are the parameters which we take it from the existing force fields. So first thing what we have to do whenever we start with GCMC simulations, we need to see that the sigma value and epsilon values which we choose for all the atoms in the system is actually representing the system. Right? So these are the very important assumption. I mean to say that has a look for. Third one, what we kind of like have to give is the temperature of the system, which is an input, and then chemical potential or pressure, whatever, because both are related. The last one we kind of like give what kind of moves we wanted and in what ratio we want to do. You want more insertions, more deletions, more translations, more rotations, right? It also depends, because why I'm saying is that sometimes rotations makes no sense when we deal with a spherical molecule, because when you kind of like move a spherical molecule, it will not affect energy in any way, right? So like that, so these are the 4 very important things which we have to consider.
Thank you so much.
Yeah, especially the crux of the problem is selecting the force field. Anything? All good? Yeah. Okay, with this, yeah, we are done for today. I think, not today, I mean like for this session. We will go for a tea break, I guess. Yeah. And see you back at 4 o'clock.
Ready? All right, okay. So I'll be talking about process modeling, mathematical modeling basics, and this is a little bit different, algebraic differential, and I thought I'll club differential algebraic also as part of this. So this has got a little bit of more fundamentals that you have done at your undergraduate and graduate level, but slowly I will build onto it. And today and tomorrow's lecture, I will try to give you an idea of how the solvers are built for the commercial solver, because these are the solvers that is running behind the scene in Aspen, AdSim, Aspen Custom Modeler, Aspen Plus, also MATLAB, Pyomo, and all those solvers. So I basically wanted to give you a glimpse of it, but I am not going into too much details into it. So feel free to ask me questions, or if you want more details, let me know. I can actually add on more materials tomorrow. So I'm pitching at a level that would be understandable more from how these things are implemented from that perspective, okay? So first concept is dependent versus independent variables. So when we declare a model and we write some equations, the question is which variables depend on what? And you have done those degrees of freedom analysis, but sometimes this becomes confusing when you are using a software like Aspen where some models has been built. If you are the one writing the equations, you probably count it, like you'd say, okay, these are fixed variables, these are free variables, and count, and this I must fix it to make the degrees of freedom equal to 0, and that's how you go. But this is not obvious in a simulation environment, and over the years I have seen this is one of the biggest confusion that arises. And you will see that how Aspen treats it, what Aspen tells you, and what really happens. And those are the things we want to understand. So first is, really independent variables are the time and the space. These are the really true independent variable always. In addition to that, there are input variables, right? These are not necessarily to be confused with inlet. If that is not necessarily an inlet, we call it input or specified variables. These are also independent variables. The way to understand what is independent variables is something that does not depend on the model. It is you who can specify it. Like for example, some feed is coming into the system, it has got the compositions of so much of CO2 and nitrogen and oxygen. That is completely independent of the system because that is coming from somewhere else, right? Same way, when the feed is coming at your boundary and it comes at some temperature, temperature is an independent variable, right? Because the temperature, that does not really depend on the model itself. It's actually at the boundary, it's completely an independent variable. Now, I will ask you a question. Is the flow through the system an independent variable or a dependent variable? Anybody, take a shot. So I have a flue gas coming through and going through an adsorber or anything, or membrane separator, and we're saying, okay, this is coming at the boundary and this is flowing through the system. Is the flow rate through the system, like meter cube per hour or mole per second or whatever, is that an independent variable or a dependent variable? Dependent variable. Because, anybody who answered dependent, can you explain? Right, because I have a system there, it does not mean that I want to send so much of flow rate, it will go through the system. It really depends on the pressure drop of the system, what is my driving force in the system. So it is not. But the pressure at the boundary is an independent variable because that is coming out from somewhere. If I want to raise the pressure, I have to put a compressor or a blower or something, but the pressure at the boundary becomes an independent variable, that I'm saying it is coming at that pressure, but the flow rate is not. So you have to be careful in terms of what you specify, and tomorrow and day after, you will see that we'll be actually discussing more with this. So when you look into a software like Aspen, you will see that it treats these variables as 3 different kind of variables, and I will be discussing more of those, and we'll be discussing these. One is free, another is fixed, another is initial, another is rate initial. So we understand that these independent variables are basically the fixed variables. That is what we are talking about. And then there are differential and the algebraic variables which are dependent variables. Okay. Now you notice that here the thing to get a little bit confused here is the free, initial, rate initial. If you have a time derivative for any of these variables, there could be 2 different types. So if I have a variable dy dt, then this variable y can be declared as an initial variable or a rate initial variable, and we'll discuss what does that mean. But other than the differential variables, all other variables are treated as the free variables which you will be calculating. So when you write the equation, then you count all of your equations and number of variables and say, okay, now it is squared, or you say there is no degrees of freedom. This is a problem when you actually use a software like Aspen AddSim, because you drag and drop a block and you think it will work out. In Aspen Plus it does, because Aspen Plus does not give you, let you specify any other variables than you can do. So for example, if you have 2 degrees of freedom, there are 2 blocks that you will expose to you. There is no way you can play with it, and or you can do anything with it to make it non-squared. But AddSim is not like that. Aspen AddSim will give you a lot of options there. So it's in some ways it's a free tool. So you have to understand what you are doing. So that's what we wanted to be clear here. Now there are 2 types of model. Again, we all know, and why I'm going into it, and that has to do with respect to the solver. And that's one of the big thing. And Aspen actually solve things very differently than many other solvers. So we'll talk about that. Those who have used MATLAB and who have used Python, there is a different way that Aspen actually treats this solution. So we'll talk about that. So first is the linear functions. We have, first thing is additivity. So that's important. So this is how it is given. And then we have the homogeneity, right? We understand these are the linear models. Anything else that does not satisfy these, like which are not linear, is called nonlinear, right? This is the best way to define it, because everything else is nonlinear that does not satisfy these. Now, what we see here is that most real world processes are nonlinear. Does that mean that we cannot come up with a linear approximation? Absolutely we can. In a neighborhood of an operating conditions, we can approximate many nonlinear models as a linear model, and they work pretty well, but within a defined conditions. And you have probably all studied that how to do it and around a neighborhood of some points. And generally one of the things we do is the Taylor series expansion, and then we can actually come up with a linear model for that one. But the reason I'm saying here is that based on the complexity of your model, you might like to make linear approximation. Many processes can be very nicely approximated as a linear model, makes no difference in terms of the results, but your complexity actually goes way down. So my suggestions always, like even with all the advancement, is that if you can make a linear approximation, make a linear approximation. Okay, but in this case, you will see that there are some high nonlinearity where if you make a linear approximation, there will be a lot of error. So in that case, obviously, we cannot do that. There is also the other questions is the lumped parameter and the distributed parameter model, right? When you do the lumped parameter model, the only independent variable is time. We're basically saying, I am ignoring the variation with respect to space, okay? When you think about an adsorption process, and we'll be going deeper into it later on, but when we think about an adsorption process, there are a lot of changes happening with respect to the space. But if we are saying, yeah, there is a process where there is not much change happening with respect to the space, I can always use it as a lumped parameter model, right? What is the advantage? It will, if you just approximate this as a independent of the space, it becomes an ODE, right? So what we really do is, in some sense, that everything has been dependency of all variables have been lumped into the form of a single variable, we are saying, with time. So nothing changes with respect to the space. Like we always say, CSTR is a good example. And we always get confused, like when we read in the CSTR, and you go to and walk into an industry and you keep thinking about which reactor in this process is a CSTR. right? It's confusing. And in the book, the first chapter, we start with a reaction engineering, say, oh, this is a CSTR. Which one is a CSTR, right? You always keep thinking about it in real life, right? But the idea is that there are many processes which can be approximated as a CSTR. And that makes you very simple way of thinking about it. Can anybody think about a very common application which can be very well approximated as a CSTR, or a lumped parameter model will work pretty good for those type of things? Any example? Like in real life, we always use, we use at home, we use everywhere actually. Also industry, anybody? Generally ignition or the combustion processes. Many combustion processes, because it is actually instantaneous, and if you are really has a well mixed systems, it will be almost instantaneous. After that, the temperature can vary, but the compositions, it comes there, it will combust, it will immediately produce CO2, like our cooking, right? You are combusting the natural gas, like you are burning the gas, and immediately after this it is CO2, mostly CO2, and there is not any change with respect to the space. After that, you can just consider a heat transfer problem. So front part of it can be approximated as a CSTR. After that, you can simply do solve a heat transfer problem after that. So this is the way of practical modeling. But in here also, I will be talking about some types of adsorbent beds, not the fixed beds, but some types of beds can actually be approximated as a CSTR. Those are like things like a bubbling fluidized bed, right? That's another technology for adsorber that can be considered as a lumped parameter system. Any question so far? Clarification? Okay. Now, if you go by the lumped parameter system, the order is given by the order of the ODE, right? So if I am saying that it has got an nth order system, this will be described by nth order ODE or by n first order ODE. This part is, we study this, but I have found it to be many times confusing, because sometimes we actually use a second order or a third order ODE here, but that may be because I'm lumping different mechanisms together. So in first order, but I just lumped it, and I'm just observing it as a nth order system. That's the way we do model it, but mathematically it makes sense that if you can actually replace that as in first order ODE. In Aspen, this gives you all the opportunities, but there are pluses and minuses, and that are the things that which we'll be talking about. It's not straightforward, like we say that, okay, if I have an nth order system, I have a second order system, and I can approximate that within first order ODE. It's not, mathematically they are not equivalent. They will be, numerically they are not equivalent. They are mathematically equivalent, but they are not numerically equivalent. So those are the things that we need to keep in mind actually. Now this distributed parameter model, the process variables will vary with spatial location, right, as well as time. And so what happens is, like when you think about an adsorption bed, and we'll be discussing more with this, something comes in and that adsorption front actually keeps moving forward, right? So the front actually keeps going forward through the system. So this is actually a distributed system. This makes it very confusing when you try to use it for optimization, because it is inherently a dynamic model. I'm not sure how many of you work on dynamic optimization. Do any of you work on dynamic optimization? Okay, so as you know, that dynamic optimization is actually complicated and difficult and involved. But if I give you an adsorber model and I say, yep, optimize this system, you are solving a dynamic problem. There is no way you can solve a steady state optimization like you open up Aspen Plus and optimize it. Cannot do it actually. So this makes it complicated because of the distributed nature of the thing. So I'm not sure. I missed Dr. Datta's presentation, but I think a little discussion about the adsorption bed is in order so that you connect dots why I'm talking about this. So this is kind of an adsorption bed. So the feed goes there, and this is actually so CO2 rich feed, and we say CO2 lean product, right? This is goes out. So this is how it goes through the system. So this is a front that moves through the system. So what happens is each location, the loading changes with respect to the time, and then this all the variables changes with respect to the space. So for adsorption system, this is inherently dynamic system. There is no steady state for an adsorption. It cannot be approximated as a steady state system. So it goes under the distributed parameter model. Okay. Any questions so far? Okay. Now, other thing is continuous and a discrete time model, right? When we mostly will be discussing about the continuous time model, like this type of equations. We say dy dt equal to f of y x theta t. So this is the type of a model. The problem comes there is that when you go to an experimental system and somebody measure one of the variables like these outputs, they will give you it as a time series data. So if somebody is observing the composition here, so it will say product composition, right? And this is with respect to time. So we'll say T0, T1, T2, T3. They will give you Y CO2, Y nitrogen, Y H2O, and all of those, right? So you will get all of these data. So this is our observation. Even though it's a continuous, actual process is continuous, our observation is discrete, right? So that is what we'll talk about this. So it becomes confusing actually that how can you actually represent this discrete time data with respect to continuous time? Because, and this is the reason why you have to be very careful about here, is that Aspen will not necessarily give you a particular solution at those points, not necessarily. So this is the problem. So when you are solving y with respect to t, say Aspen gives you a solution like that. This is what we call a breakthrough curve. Your data points are basically here, here, here. So what you can do is after you solve the problem, you can just plot it and say, oh, my model is not working well or working well, whatever. But if I ask you that take these 3 points into considerations in this particular time and solve an optimization problem to obtain the parameter of a, say, mass transfer coefficient parameter, then I'm talking about getting a solution at these exact points there. How do I incorporate that in the solution? Because Aspen is solving continuous time, your observation is discrete time. So how do you connect both the dots? So that understanding is actually important for you. You can actually plot it and say, oh, my model did not work, but can I improve it by taking that into consideration? It's almost like you do trial and error, but is there could be systematic way that these discrete points can be taken into consideration and for estimating or optimal estimation of parameters. So that's why it is important for us to understand this. Yeah, so the issue is that in a computer controlled systems, often what we get is sampling of the variables are at discrete point of time. does this overall approach has got any method, any merit in it actually? So we always say that this is a continuous time and Aspen is solving it in continuous time, or any solver like MATLAB is solving or PyMO is solving at continuous time. Is MATLAB or Aspen or any other software, can it solve it continuous time? Does it solve continuous time? Anybody? It does not, right? It has got discrete interval at which it is solving it. So it does solve it, but how do you tell the software you solve at this particular point? Because I'm interested in those particular points, right? So actually the thing is the real physical system is continuous unless you get an analytical solution which is not practical. It is always, even with those software, it is discrete. It is that it actually connects these lines depending upon whatever software you are talking about. It makes it either like a cubic interpolations or a locally linear model. That's why it actually looks up like that. It seems to you that it is continuous, but it is not. Behind the scene, it does not have the information. So just to ensure, when you look at a plot, do not assume that it is doing something continuous. It is not. So real life is continuous. Our observation through a computer controlled system is discrete time, and our solvers are also discrete, doing discrete calculations. Okay? Okay. So how do we set up this type of a model? Right? First is this input-output type of a model, this one. These ones are the most simplistic. Basically, I am saying I don't want to understand anything that is happening. You give me the input and output, and I'll give you some of the, give you a predictions. Like for example, a lot of machine learning models are like that, right? We are basically saying, you just give me the data, I will fit it. I don't want to understand what is going on. I'll give you a functional relationship between input and output. We use these type of models for process control, as you have all studied quite often, and now a lot of artificial intelligence, machine learning, data-driven models are all in this domain that which we are considering. But we are not interested as part of this class on this side. We are interested in these models. So essentially what we wanted to do is a state space model. We write it as a continuous time, that's what I highlighted it here, and then this will be all distributed parameter and nonlinear. So this is the class of the problem that which we are trying to solve. So remember that I talked here about the continuous time. That is because how we write the equation. The problem, the solution technique is different, but this is what exactly what we will be solving or writing the equation as part of our work. Anything, any clarification? Okay. Now, I already said that we have got the order of the system is actually very important. So first order means that we have one differential equation. Second order, we have got two first order, and third order, and so on and so forth. So what we do there is that first thing, and the simplest one that you have studied mainly in your controls class and solved it, and this is something you can actually solve it very easily in a software, like if you are using one of the ODE solver like ODE 45 or 15S or anything like that in MATLAB, you will be able to solve this problem easily. Now, what are the things that we are actually talking about here? So let's be clear from an adsorption process what each of these variables mean. So this X could be all these composition variables over here. That is, if I say, when I say composition variable, composition of what? Composition of which type of species? Is it gaseous? What else? also the solids, right? Because the solid loading is changing, because we need to compute that. This is the difference compared to other processes, because I'm actually changing the loading as the gas, as the molecules are moving from the gas phase to the solid phase. So the solid compositions are also changing. But there is a catch here. Only the gas flows through the system, solid is stagnant, solid is just staying here, right? So we'll be discussing that how do we model those, but that's what we are actually doing here. So this could be all the compositions, and then we have these U, which could be your other things, like for example your compositions, the flow or the pressure or temperature or anything. And then these disturbance variables could be something which you cannot control. For this work, which is just focused on the simulation, we do not really distinguish between this type of variables and this type of variables. For us, everything is something that is, we fix it, right? And the other things we are calculating it, okay? Now, what is the one of the first type? The linear lumped parameter continuous time. I'm now actually keep moving here, is that like go to the second order state space model. There are two equations, and it immediately becomes more complicated. And when you look into this, so what is the issue here that is coming, and I'll talk about that in a moment here, that you have these two variables. Now, if I'm actually considering it with respect to the space, and I'm trying to come up with the compositions at each of these locations, and I find out what is the thing that I'm trying to come up with it, so we have to write many equations, and then these only time derivatives are not sufficient, because this is a lumped parameter system that I'm writing here, right? So this is not appropriate for writing an adsorber, but this is a simplistic model that I think practically all of you have solved as part of your undergraduate class and part of the graduate class. So we know how to solve all of these, right? So so we just write it like this, and this gives you a state space form. I wanted to show you this one because this is our favorite equations we always used in the controls class, and I was very happy about it. And they say, okay, this is a standard state space model, and I control it. So we'll actually divert from here to say that, okay, when this is the picture we have gotten. Now, yeah, so this is the picture we have gotten. Now we go to the actual process model and see how the real process model differs from that simple description that what we had. First, think about how we write a process model. We write simple thing, accumulation is equal to in plus some generation minus out minus loss, right? That's the standard way of writing that one. So if I'm writing this for the mass, we said accumulation of the mass is whatever is from the in minus out, right? And then species conservations, we say, well, whatever is the generation of species A and outlet, rate of species A at outlet minus rate of consumptions of the species A and all those stuff. And then we write the conservation of energy in the same way, right? That energy in, out, and generation and loss, all of those things here, right? We can also write momentum conservation equations or the pressure drop model, right? Those things as part of this. But one of the things that what you really need to think about it in general in a simple classroom type of a project, we don't write that, is other constitutive equations. First thing is the physical properties. This is where the strength of a software like Aspen comes in. Otherwise, you can use MATLAB or Python or anything for this. The first thing is this physical properties. So physical properties, for example, if I do the viscosity model, thermal conductivity, diffusivity, surface tension, these are our transport. So how a molecule is getting transported inside the adsorbent, how the CO2 enters the locations where it is going to be adsorbed. So some of the CO2 getting adsorbed, some actually flow through the system. How should I describe it? What mechanism by which it goes, right? So in general, if we think about the transport mechanism of molecules, what are the typical transport mechanisms of molecules? Can anybody tell me? Generally, how do we model it? What are the transport mechanisms for molecules within a solid? So if I think considering a gaseous molecule, and the gaseous molecule is getting inside the solid, by what mechanism would it go inside the solid? Diffusion, yes. What else? Sorry? I heard capillary, okay. What else? Yeah, that's how the water gets into a lot of the rock structures also. What else? Actually, it can be very complicated. It really depends on what that molecule does with respect to the solid and how it interacts with respect to the solid. If you think that the transport essentially takes place only in the form of molecule, then diffusion and the diffusion induced convection, local convection, is the real mechanism by which it will flow. But depending on what our other species gets formed, the mechanism can actually greatly vary. Like many times it can actually form some kind of a charged species, and it can actually jump from one location to the another locations. So internally, how the overall energy works out and overall transport mechanism works out, that depends upon in what form the molecules get transported. Is it essentially only molecular transport, or it is going through some other spaces? We'll be also discussing some of these kinetics here in more detail, so I do not want to spend more time here. But the point here is, these physical properties model, what type of equations do we write for these? These are differential models, these are algebraic models, or what it is? Let's focus on these one first. The transport properties model. So what type of model equations are these? We heard differential. We heard something else. Go ahead, don't feel shy. Yeah, but if we just simply go by the property, right? Like for example, if I say go by the diffusion coefficient, then we write an algebraic model for diffusion coefficient. But when we describe the mechanism, that how the diffusion takes place, it's a differential equation, right? Similarly, when I'm looking into the thermal conductivity, that model is an algebraic model. But when I'm saying how the thermal conduction takes place, right? If I say that okay, we are using Fourier heat conduction law, then it becomes a differential equation, right? So it can be both ways. So these properties, which is basically all the model that Aspen will be pulling for you for the species that we are interested, it will pull lot of these algebraic models. So when I say these are all becomes your algebraic model if you are just focusing only on the properties. This is one of the big things that which we need to discuss, the thermodynamic property model. Now, what is the parallel of a absorption with respect to adsorption? In absorption, AB, absorption, that is liquid gas, right? The equilibrium is between vapor and liquid. In adsorption, the equilibrium is between the solid and the gas, right? So in adsorption, we have already okay, vapor liquid model. How do I represent the vapor liquid model? We have a activity coefficient model. Like there are only two models that which we use, right, for vapor liquid equilibrium. Either it follows Raoult's law or it follows Henry's law. And then using the Raoult's or the Henry's law, we then write in form of an equation of state, or if it is some liquid that does not follow the ideality, we use an activity coefficient model, and that's how we actually go for it. For adsorption, you just had the class before, so we write the isotherm model. So it's a completely different way of thinking about it. It's instead of that equation of state, we actually write a isotherm model, but that's an equilibrium model there, right? So, however, I still write equation of state under the thermodynamic model, and you can come to me and say, what are you talking about? This is not in a gas solid system. We are not talking about an equilibrium in terms of equation of state. This is only for absorption. So why are you using, why we need an equation of state here? Anybody? Do we need an equation of state in an adsorption model? Take a shot at it. It's a thermodynamics. We'll go all over the place, right? We'll go to the math, we'll go to thermodynamics, mass transfer, heat transfer, fluids, everything actually. So let's think about thermodynamics. So equation of state. Do we need equation of state? Where? Why? Right, for the molar density we need that. What else? Gas properties, like which properties? Yeah, pressure temperature changes, and so the density is one of the things that is we need. Another thing which is equation of state is absolutely critical for that. Temperature. So what is the equation of state used for? Say that. Be loud. Be loud, please. What do we calculate by equation of state for gas properties? You are right, for the energy we need that. But what is the thing? We use it for excess enthalpy calculation, remember? Like the delta H excess, like we have got, when we write the enthalpy model, we write it as an ideal gas, plus we have the non-ideality. How do we calculate the non-ideality? This is all given by the equation of state. So if you are using SRK or the Peng-Robinson or any other equation of state, that's the guy that is used for calculating the delta H excess. So we are not saying that unless I say this is an ideal gas, if I say it's an ideal gas, I do not need an equation of state. But if we say this is a real gas, right, so we will need this equation of state here, right? The same way we might be needing the vapor pressure, and if we do not have the liquid here, so anything related to liquid, we can actually ignore this. But this is a general list of it that which we are considering here. Now I said here chemical and the phase equilibrium. So chemical equilibrium, do we need it here for anything? For a typical adsorption, right? Let's brainstorm. Do we need chemical equilibrium for considering anything? If we have a chemisorption, right? If we have a chemisorption, we might need to describe the chemical equilibrium. So an isotherm model is an approximation. Sometimes it is confusing. You say, oh, my system is undergoing chemisorption. I could fit this isotherm model. What are you talking about? Where is the chemical equilibrium coming into picture? That is, as I said, that's not a true representation. It's kind of a isotherm model. You have to kind of think about a data-driven representation of it. It does not necessarily tell you anything about the mechanism that is going behind the scene. That the same solution you can get from a more mechanistic model. And if time permits, I will actually show you the parallel. Actually, one comes from the very fundamental level, and another is, I will just simply show you an isotherm model that will fit to the data. Perfect fit. But that does not tell you about anything that is going behind the scene. So all those things are possible because the chemisorption is very complicated. Very complicated. The fact that you could fit an isotherm model does not mean that you understood really what is going behind the scene. So it will work fine in mathematically, but in terms of mechanism, it might not say this. So we may need chemical equilibrium there. So what happens is that one and also the kinetic rate equation, like when we use an Arrhenius type of rate equation, right? Like we said, reaction rate is equal to A exponential minus E over RT, that type of formulation there. All of these are my algebraic models. So just to ensure we are on the same page, these conservation equations, these are all given by differential equation. Remember at the end of Bart Stewart Lightfoot and all your transport class, right? All of you taken that all these equations that you have done in your transport class, those are all differential equations. Those all goes here, right? But at the top of it, there are other equations that which we need, so which are all these equations, and that is what goes into the picture. The reason I'm actually getting into a nitty-gritty of it, because when you actually do Aspen AdSim, behind the scene it will actually keep pulling lot of models here. You will not realize what it is pulling, right? So you have to understand it. The problem is, do you need to understand? Yeah, absolutely we need to understand. We are all researchers. We need to understand what it is pulling behind the scene, because otherwise when it will fail, or the results, I cannot interpret the results, or I cannot modify, right? That's why we need to do this. And then there could be other equations specific to a particular system that we need to describe that particular system, okay? This one, okay, I'll leave it. So yeah, some font here probably is not right, but you can understand it. So this is an example problem which I will be working tomorrow as part of our workshop. So I thought I will actually describe it today, and then tomorrow we are ready for our workshop, and we'll be modeling this, and you will see that how these equations it brings, and in Aspen how you actually model these things, because AdSim is built on this framework. That software on which it is built is Aspen Custom Modeler. So we'll be discussing that here actually. So let's think about it. This is a reaction that is taking place between methanol and acetic acid, and this is the reaction. Let's, for simplicity, we'll consider isothermal systems for this one. So if I consider a species conservation equation, I can simply write it, and this is for a CSTR, F in and this is out, and then this is plus minus reaction rate. It depends upon which one we are writing, which species we are writing, what is J, whether this guy, this guy, this guy, or this guy, depending on the sign will change plus or minus. If I'm writing setting the derivative equal to 0, this is a steady state, this becomes an algebraic equation model. So this becomes only this. So remember what I said, it's the species conservation, it is really the conservation equations that gives you the differential model. There could be other differential equation. I'm not saying there cannot be other differential equation, but mostly the source of the differential equations for process model are the conservation equations, but then there are others as well. But this is the species conservation, and for a CSTR, if I set this to 0, like for steady state, then I do not have any differential equation, because all other properties model and everything, these are all algebraic equation. So the overall equation, system of equation is algebraic here. If I write this one, it will lead to, this is a differential equation, and then other models like the properties models and others are algebraic, so it becomes a DAE model. And we'll talk about this tomorrow, how to solve this guy, but today I'll be focusing on something else. Now, what are the other equations that we need to consider? One is the summation of the mole fraction we'll be considering. Then we'll relate the concentration to the density, okay? And then we'll have the specifications for all the properties, right? So we'll write these equations tomorrow in Aspen Custom Modeler, and I will show you really how to solve it. So what I wanted to show here is, one thing I wanted to tell you here is that there is a fundamental difference between how you solve these algebraic equations like in a solver like MATLAB versus Aspen. And so keep these things in your mind. If you have never used Aspen Custom Modeler, like which is what the AdSim is built on, Aspen Custom Modeler, the solver solves everything together. MATLAB doesn't do that. In MATLAB, you have to call a routine like fsolve. You say solve this system of equation. But for Aspen, the solver comes at the top of it. So it basically grab everything and solve it. So you don't need to worry about it. You do not need to say solve this one, this is my initial guess, this is this one. You don't need to tell anything. It will automatically grab everything and solve it at one shot. So that's a fundamental difference between those. So what you will see, we'll just simply write all of these equations that what we are talking about. It's part of. Now, in this case, out of this total discussion, what is the properties model that I need to write here? So I will go over this equation again. So remember what I said, I have to write a species conservation equation. This is what we wrote here. Then I write Rj, this equation we can write, okay. So look into these two equations. If I write this one, and then I assume that you are substituting this equation here, and then we are writing this mole fraction, and then we are connecting this to this, right? What properties model do I need to consider here? Properties model for what? Do I need any properties model? Let's think about it here for this simple problem. Like I was always saying, yeah, we must use equation of state and all that kind of thing. And I give you this example, and you can come to me and say, yeah, why are you using properties model here? Tell me, are we using properties model here? Do we need equation of state? Here, do I need to specify anything, or it will go forward? This guy, remember we talked about this, the density? Yeah, that's why we need to have this, because how do I know what is the density of this material, right? So we have to have a properties model, right? Now, then, so the plug flow reactor, the CSTR was an algebraic equation. Now we expand it and we say, okay, let's go to the plug flow reactor. And here we write this equation, the standard equation here. And again, you are familiar with these equations. There are many different ways this is written in terms of V and X and Y, and this goes on the other side. You are familiar with this. But this is immediately it becomes a differential algebraic equation. So I need to now think about how do I solve this combined system of differential and algebraic equation. Then obviously the other equations are similar to the CSTR model. The moment it comes here, it brings a new complexity. I said here you need a boundary condition. So for this equation, can anybody tell me why we need boundary, how many, and what conditions are appropriate? Okay, so how many, sorry, how many boundary conditions do we need? Somebody said something. And don't be afraid, just say everything is right. No, this is a workshop, we are working together. Say anything you like. Nothing is wrong. One, right? It's a first order differential equation. We just need one boundary condition, right? What should be the boundary condition? Sorry? So just like we did a plug flow reactor, right? So this is a plug flow reactor, typical one. And we are saying something is coming in and this is going out, right? This is a PFR. So in these equations, what boundary should I provide? Ci we provide, right? So we have got, like I said, 4 species. So we provide for all 4 species, right? You see we have, we have got 4 species here, right? So do it for 4 species. So I say I is equal to 1 to 4, right? And then what else? Do I need to provide still anything else? Yeah, also U, right? Because if I wrote it everything inside here, right? And if you are saying that you can change, again, you can consider this to be constant and not changing. That's okay. But if you have that, otherwise you have to provide the U values also at the inlet, right? So those are the thing which we provide. The boundary condition. This is an important thing, and when we look into the Aspen adsorption model, we'll be talking about this. A lot of these things are actually difficult for the desorption part. What I have realized is adsorption is generally can be straightforward and easy to understand, but the desorption can be tricky actually to understand it. So we'll talk about that. And then we have the additional equation as the CSTR model, right? Now, now we wrote two type of models. One we wrote algebraic equations, another we say differential algebraic equation. Now how do we solve these models? This is the next part of it, right? This is the most important part, right? You cannot come up really with an analytical solutions. I know we at part of our graduate class you have solved, like for the transport class, when you have solved the PDE problems, right? Combination of variables or separations of variables, all these methods, you have solved only one equation there. Now if I give you 10,000 equation or I give you 1 million equation, can you solve it actually? There is no way you can solve it analytically, any of these. So you have to solve it numerically. So question is, how do you solve? And most practical chemical engineering systems are numerical approach is the only approach, right? You can come up with only numerical approach. Now, the standard approach is that, remember we have the spatial derivative like this one. This derivative with respect to the space, right? This derivative, the standard approach is that this derivative is discretized using one of the finite difference schemes. So when you will use Aspen, you will see that it will give you the opportunity to call one of such finite difference schemes. So let's see what are those and how they work, right? So if I have a first order derivative, sorry, this one a little down, so you can hopefully you can read this. This is a first order derivative. So the simple one is the forward difference method, right? So f of x plus h minus f of x. This is the backward difference, and then we have the central difference. These are the three approaches that which we can use for this. So where should I use these to look similar? So where should I use forward difference versus backward difference? So for example, this case, this one, should I use the forward difference or the backward difference? Looks equivalent, right? Sorry? And the because? Right, let's look into it numerically what happens, right? So if I start at this location, right, I'm marching onwards, right? So it is saying that if I'm actually solving it, say I'm discretizing it like 0, 1, 2, 3, like that. So this space is being considered is bunch of discretization. So if I'm applying this equation, and I'm saying if I do it at 0, right, we are saying f of, at this point we are saying f of x plus whatever it is, right, h, meaning this will be at the 1th location minus f of 0. So that basically means f of 1th location minus f of 0's location with h. So it works out fine. There I have no issue here. So what I do here is, I just provide the boundary condition here. So this becomes my boundary there. So if I'm doing it with respect to concentration, so this is my inlet concentration, or this I gives it in terms of the velocity, concentration, temperature, or whatever. So I'll just specify it and it will be fine. But what happens if I try to use a backward difference with the same scheme, that if I'm actually trying to do it here, you say if I do it f minus 0, then it will say f0 minus 1. So it's kind of pushing on this side. So it doesn't work out that way. So that I will apply when I'm actually looking into this side of the boundary. So really, the cases where this flows comes, one flow goes this way, another flow comes this way, I will probably use a forward difference this way or put a backward difference this way. Or I have to rotate the axis. I can shift everything one forward to apply those. Why this is important here is that adsorption processes, and we'll discuss that later. I just wanted to use, these are the outlets, so this one coming here. Adsorption and desorption actually switches side. So this, from the side the adsorption gases goes, ideally the desorption system, the desorbing gas will enter from the other side. So if you are doing the discretization yourself, it does not matter which is your 0 and which is 1. I can just simply rotate it and say this is my forward, but you will have apply one side forward, another side will apply backward to be compatible with this. They are similar and their order is similar, but it really depends upon where you are setting your axis and where is your boundary. Now, is this understood? Anybody needs any clarity? Okay. Central difference, yeah, it has got better accuracy. So why don't we use central difference all the time? You will see people actually hate using it. I already gave you the hints that there is some issue here. What is the issue in using a central difference? Right, because you have to kind of see this is really gives you a plug flow, right? F1 depends only on F0, F2 depends on F1, and so it will be actually marching like a plug flow. When you look into this, so if you look into that one, if I'm applying it here, so this one, say if I'm considering F2, right, it is not only it is F0, it is going to F0. Then when I'm doing F3, it will become F1. So this crisscross way it compels that the whole thing needs to be solved together. What is the problem with that? When it comes from a solver perspective, when you actually do the matrix decompositions, and I'll be talking about that a little bit later, from a linear algebra perspective, this thing will come like a banded structure. It will be coming like this actually. So it is easy for you to solve it like this. Because I can independently solve this guy irrespective of what is happening here. So it will be actually a banded structure that at which will show up. It's easy for the linear algebra perspective. But the moment you do this, this will make your solution much more complicated. So as you know that in the fluid dynamics, like if you any of work with the CFD, this leads to an oscillating flow actually, and you have to be very careful to stabilize it. So the solutions can be very oscillating for when you try to apply this. But nevertheless, you can do it. Now, the second order derivatives also the same way. So you can do second order forward difference, second order backward difference, and the central difference. And then these ones appears in case of, like you will see, okay, that probably cut, but I'll tell you this. When you are doing the Fickian diffusion, this actually appears for the transport within the molecular species transport within the solid. So in that case, that's a second order differential equation. And then you will, when you try to apply the discretization, so an Aspen does it behind the scene for you, but it actually applies one of these methods based on what is specified, because there are second order equations, and we'll be describing those as part of ADSIM what it does and all of those. But these are the second order derivatives because we will be considering Fickian diffusion within the molecules and based on whatever mechanism we consider. The other one, the same things, the energy conservation, Fourier law also does that, and the dispersion also requires you to consider a second order model, right? Remember the dispersion equations is given by some k terms d2c dx2, right? So this is a second order equations, again can make your life miserable in terms of solution, but this is also used for second order. But so once you approximate these derivatives as in form of a algebraic equivalent, it converts everything to an algebraic equivalent. Just want to ensure we are all on the same page. So the technique is that when you have these differential equations with respect to space, you apply one of these forward or backward or the central difference. These are all finite difference schemes. The moment you use the finite difference schemes, these derivatives are replaced with these algebraic equations. That means that now you will be solving only algebraic equations. Is this clear to all? Because I'll be going forward there with. So in Aspen, when you solve it, the only thing you would like to solve is the time derivative. Is it not possible to use a integrator here and as well as for the time? Yes, you can. It just makes it very, very difficult because there is an inner nesting loop that has to work out. But in Aspen, that's not how it is actually done. So I'll talk about that more. So all the spatial derivatives are discretized to convert those derivatives to algebraic models, and so that already properties model are algebraic. We are converting these to algebraic. So I will only solve algebraic equations. Okay, so now how we solve this? So first is, again, I'm sure in your numerical methods class you have done a lot of those, but I would like to say a couple of things here that we have to be considering as we move forward. So first is when we solve the system of equation, everything is actually of this form, right? So f of xk equal to 0, I want to solve it. So this is the approach by all the implementation that you will see. These are all derivative based approaches, right? So in Aspen internally, they do not use any derivative free approaches. There are some newer generations approaches that are showing up, but all approaches that you will see as part of ACM and ADSIM, these are all derivative based approaches. So they all are variants of Newton's methods. So different flavors of Newton's methods, but they are all derivative based approaches. So how they work? So this is the derivative. So xk plus 1 is equal to xk plus alpha k pk, and then we say gradient of f of xk pk is equal to minus f of xk, right? Now, don't get confused here that these are all greatest solver, but we can only find the local minima here. So if you have a multiple minima, you have to use some of the global solvers, and we can talk about that more. But with these solvers, it will only find the local minima, just like as you will see others. These are in linear equations. You can clearly see that if I have got so many of these, so I will have, this will be the size, this will be n by n, and I will be solving for all of those there. So ultimately what you are seeing here is we started with a differential equation, then we converted that to algebraic equation, we said those are nonlinear, but then finally we are solving a linear equation. So the guy who brings all the capability of a solver is linear algebra. All the strongest linear algebra solvers, and it's still very old. All linear algebra solvers are still very old, or everything in MATLAB, in Aspen, still very, very old. There is no modifications there because all the greatest development that has happened in linear algebra, those are all there. So behind the scene, at the end of the day, I need to solve the linear equation. So remember here, even for Aspen AdSim, doesn't matter whether you are solving an integration problem, nonlinear equations. At the end of the day, you are actually solving the linear equation. So when you will see in solver in Aspen custom modeler, it has got bunch of settings for the linear algebra solver. It has got bunch of setting for nonlinear equations, but that is completely different thing. So when we go there, we'll describe that. But let's see that why we cared about the linear equation solver. One thing is that we need first derivative. I'm not sure how many of you have heard about AD or automatic differentiation. Okay, so so if especially if you're interested, read this. I'll not get into that more here, but Aspen does not still employ that, but this is known as automatic differentiation. This is an approach by which you can calculate the derivatives. Aspen still considers derivatives to be numerical derivative calculation. So these derivatives, all the Jacobian calculations are still considered to be only numerical based. So what it basically means is that if I'm actually it basically comes from the fundamental properties of anything, right? So if I'm trying to calculate this derivative, I'm simply saying f of x plus delta x minus f of x, right? And then I'm doing the delta x. Technically, this is delta x tends to 0, but this is the overall approach. And then you have gotten these small steps that you take, and then they try to calculate it numerically for any of these things. And this is actually the root of all problems. So these approaches are very good, but this derivative is a local approximation. So because these derivatives are not accurate, based on that, you cannot make a determination how far you will go. So that is why this alpha k is less than 1 most of the cases. If we can make alpha k equal to 1, this is known as the full Newton step. If you can do full Newton step for any of these, wonderful. Only couple of steps you will see you are getting the solution. But most cases it will keep cutting step, cutting step, cutting step, and so that's the problem. So question is, I'll talk about a couple of those things here. So this method can fail. Now when we actually teach you Aspen AdSim, and you will see that it starts failing sometime or quite often, even ACM, when you actually see that you cannot actually solve it. And the general thing that which we always think of, say, yeah, the solver is not good, right? But this is really the tussle between the solver developers and the coder like us. I will write the equations and I hope that solver solves. Fact is, there is no solver in the world that can solve any problem. You have to be careful as an user. So you have to help the solver to solve your problem. So if the problem doesn't solve, look into your equations. So that is why we need to understand why it fails, right? First is, this method can fail even if the solution or the roots exist. Many times you change something and it comes up with the solution, and I say, okay, this is crap, because I just did not do anything and it solved already. So why, right? So first is, one is the poor initial guess, like where you are starting. So you have to remember from a numerical methods class that the initial guess is an important step. The reason is because I'm starting, where I am going, it depends upon where I started, right? So this is important, where I started. The other thing is that the first derivative can be ill-behaved in the neighborhood of the roots. So when you are approaching the solutions, it can become ill-behaved. Like what does it mean, the ill-behaved? Like it may not be differentiable in the neighborhood of the roots. Maybe the derivative becomes 0 around the roots, and the linear system of equations can be ill-conditioned. So when it is actually trying to decompose and solve the problem, it cannot, in essence, it does not invert it, but when it is in some sense, you cannot, if this matrix is not invertible, then it becomes actually ill conditioned. So as you are going to the roots of it, maybe it is not getting invertible anymore. So that's one of the problem here. So does anybody know, or from your linear algebra class, how such linear equations are solved? This is a matrix, right? And how is equations like these are solved? So remember, this is a standard Ax equal to b. That's what I wrote. So this is like this, equal to, so this is a vector, this is a vector, and this is the n by n matrix, right? How do we solve this type of equation? X equal to b, right? Go ahead, very good. Sorry? Okay. Anybody else? Sorry? Yeah, so most cases what we try to do is actually, the standard technique is to do a decomposition, okay? Very standard approach is actually doing decomposition. The most standard way to doing it is either doing an LU decompositions or an LDU decompositions, right? So in that case, if I'm simply doing an LU decomposition, this will be like, we put it in form of a matrix. These are all zeros, and this is the other way around, and this is all zeros, right? So this is the upper diagonal matrix, this is the lower diagonal matrix, and we do the decomposition, and that is how we solve this. You can also do an LDU decompositions, you can do the QR factorizations, I'm sure that is what we are talking about, and that is how you do that. But this LU itself, like for example, if you look into this LU decompositions, I said these are, when you actually decompose it, right, if what happens is that if anything, so like for example, if this component becomes 0, like anything on this diagonal becomes actually 0, then you are in trouble. And so when you try to get one, the L11, L12, L2, L21, L22, all of these things here, and you are in the diagonal, it becomes 0, then you are in trouble, actually. Because you cannot determine it. So because this becomes, everything becomes 0, there is no way I can determine anything about it. So, so that's the trouble that the solver is running into. And that is why it basically say, I cannot do anything about it. So that is one thing what you have to do it. We are expecting a quadratic convergence rate, like as we know from the Newton's methods, right? We need another thing, even though we are not calculating the Hessian here, this is which you know, remember for and optimization, so we do it here. But even for these systems, you can only get the quadratic convergence rate if the Hessian, so the second derivative here, is actually continuous in the neighborhood of the roots. And if it is not, then you will not get that. You will only get a linear convergence rate. It will convert, but it will be giving you a linear convergence rate. So as an user, what you can do, and we will talk about that. First is, we'll talk about how to pose the equations. I'll discuss some of the way that you must avoid posing the equation. Like the way the equations are written and derived, that's not, you should code an equation in a software. It's completely different things. Coding is completely different than when you read an equation in a book or derive the equation. It's mathematically they are equivalent, but they are not numerically equivalent. So you have to be careful there. But anyway, we'll talk about those. Now, what it does is that generally what we do is something called a, now this alpha, the way these things are adjusted internally, and Aspen actually does not give you access to many of their solver settings. Like even those solvers which seems like give you access to a lot of those, Like for example, I collaborated with Professor Bigler quite a bit, who has one of the developers of the IP-opt, right, which is used as a leading optimization solvers. And he tells, I have probably more than 1,000 parameters here. And it's only out of that maybe 50 parameters are exposed to the users. Others are set when he tried many systems and do that. So that is how it is. Aspen even actually exposes very few parameters, but internally a lot of things are going on. So one of the thing, and that is why I tell you that when it sits, it is doing something, and then fails, what it internally tries to do, one thing is that this alpha k, as I said, that this derivative that you are getting here, it's just a local approximation. So you are making step based on these, but you need to adjust the step length. So how do you adjust the step length? So Aspen generally do not have some of the other approaches that are there in many other solvers, but one of the standard approaches it follows is that what we call the backtracking line search. So what you do here is that you start with a sufficient large value of alpha, right, that we generally can start alpha equal to 1. So that's the step length. That is what you wanted to take. Then what you do is that you calculate this one, this guy, and then you are basically saying that if I am actually solving it, that basically meaning is that I want to keep this equation in front of your eyes, like f of xk equal to 0. So what does it mean is that whatever is the value that I am going, I want to go to a descent direction. So if I'm having a value of 1000 or 1000, I want to take it to 0. So what it really tries to find out is that what I have right now with the step versus what I am right now, is this new step leads to a sufficient decrease. If I had a value of 1000, is it going to like 800, 700? Because I want to take it to 0. If it is saying no 1000, but you are just 999, or it actually an ascent step, like 1001, 1002 or whatever. Instead of a descent, it found that when it took the step, it is an ascent step. You should not take that step. So what should you do? So it actually calculates that this is whether it's a sufficient decrease. If it is a sufficient decrease, then you said whatever is the value of alpha k you consider, let it be, and then you are done. Otherwise, you need to keep cutting alpha and keep repeating it. So that means that if this alpha becomes 0, you are stuck. So sometimes it will keep complaining, saying, oh, we are stuck at it is stuck at a minimum, but that it does not seem to be a solution. And that is basically what is happening, is that it cannot take the step, and when it keep cutting it, it finds a solution that where alpha k is close to 0. So it's stuck at a minima, or cannot find a solution. We are stuck at a point which is not the minima. So that is what is the problem that is coming. So how it basically what it is doing, it is backtracking. It comes with a very large value and then keep reducing it. That's what it tries to do it. This is an associate computational expense. Now the question is, how do I determine the sufficient decrease here? I'm sorry, there is an O missing here. I will correct it. Sorry for that, I just saw that. For determining the sufficient decrease, you actually apply one of these conditions. So Arimijo or a Wolf or a strong Wolf or Goldstein conditions. You will really do not need to get into any of these, because Aspen does not expose you to all of these, but internally it actually keeps checking. So when you see that it is complaining, the way you understand mathematically, at least you see that this is what it is trying to do, but it is calculating the derivative, it is trying to take a step, but it is not a sufficient decrease, and the moment it is trying to do this it is actually coming to a 0 solution. So what it basically means is that it can be related to a derivative calculations, like which is not really meaningful approximations at that point. The other issues that comes because of some of the equations become ill conditions. So both cases will lead to this thing. So another approach that is, to the best of my knowledge, AspenTech has not yet done this, but we have a trust region approach, which I will skip, but any of you are interested, we can discuss about this. It's pretty complicated, but we'll skip that one. So concluding remarks is that types of process model depends on the unit operations, what mechanism we are considering and modeling and how we are doing. You must always remember accuracy versus computational expense and the difficulty of applying different schemes that which we talked about that one before. And then finally what I will say is that you must do careful considerations of model formulation, initial guess, solver algorithm and the parameters. So when I will go over the tutorial tomorrow, everything that we discussed here mathematically, I will try to cover a lot of those things tomorrow, and I'll show you what Aspen exposes, what those parameters mean and what values you should be setting there. Okay, so with that I end here because I'm probably 5:25. So questions, any questions? We'll probably just quickly check. Was it cleared or? Sorry, do I need to? I was just trying to see if anything in the chat actually.
So,
probably not.
Any questions from the participants and online participants? You can post it on the chat box.
I can stop sharing and I can see the chat, right? Where is the chat here?
Yeah.
Where is the chat?
Dean Webex.
I cannot see where the chat is. Is there a? Yep, please go ahead. Hello. If you have a question, just speak up, please.
Online participants, if you have any questions, you can interact with Devanshu now.
Okay. All right. So please go ahead if you have a question. Okay, we're not hearing anything here. Is the overall concept clear to you all? Because tomorrow we'll discuss about the PDE, and if you have any questions, ask tomorrow. Feel free to ask tomorrow, and otherwise ask please today also. All right. Now I'm not seeing anything here.
The day starts at 9:30.